Hold on. Okay, can you hear me all right?
Yeah.
You're good?
Well, I just wanted to welcome David Brain from CU. I mean, I think one of the benefits of holding the summer school in Boulder is we have leading experts in the field in a variety of things. So David has you lectured at the Heliophysics summer school several times, right? So so routinely get him over here. Do you want to say a little bit about yourself before you get started, or?
Sure, and I actually have it a couple slides in, a little bit of intro, so it should be okay. But I'll say a little bit now. Hello, I'm Dave. The last name is Brain, and I know about 6 or 7 of you here already, I think, and by the end of today, I hope to know a lot more of you. And the last name really is Brain. That's not my fault. And Dr. Brain or Professor Brain, those both sound like evil superhero names. And so most everyone calls me Dave. That's actually my preference. I used to demand that people call me Dave, but for some undergraduate students, it makes them feel really uncomfortable. So whatever is comfortable for you, but I'm definitely fine with Dave. And this is my 3rd time speaking at the summer school, I think 2021 and maybe 2015 or something like that. I spoke at the summer school, so I'm happy to be back. And you get me for 3 lectures today. So here's hoping you like how I present things, and off we go. So you're getting towards the end of your time. And I don't want to drone on and on at you. That's not great for you, and it's not great for me, especially if I'm giving 3 lectures today. So I want to encourage you to be interactive, and I'm going to demand several times that you be interactive. It may feel a little juvenile to you at times. Please just play along, and we'll all get through it together. Next, I'm not going to go around and ask everyone to do introductions. That was in the back of my mind when I was putting this first lecture together. But Nick gave me a sense of kind of where you're from and what heliophysics disciplines are represented here. Names and pronouns I can pick up as I talk to you at lunch and break and things like that. But since we're doing comparative environments, let's at least do favorite planet, where you can interpret the word favorite however you like. So let's just go rapid fire. Okay. Favorite planet, Mars. Favorite planet? Jupiter. You know, Fran's staring at you right now, so that's good. Okay. Saturn. Okay. Earth. Earth. Saturn. Jupiter. Earth, Saturn, Earth, Mars. Yeah, okay. Venus, Jupiter, Earth. No. No. No, Pluto, great. What's that? Jupiter? Mercury. Oh, nice. Earth. Saturn. Earth. Venus. Earth. Earth.
Venus.
Venus.
If I say Mars, will you not give me my thesis?
Correct. Yeah, Rebecca was my student. Okay. Mars. Okay, I didn't hear some planets mentioned. Uranus and Neptune were not mentioned. Neptune would be probably in my top 2 in terms of favorite planets. And I don't know if the other one would be Mars or Earth, actually. But most of the community knows me as a Mars person. So I'll tell you a little bit about myself. On the left-hand side is personal, on the right-hand side is professional. I'm from the Baltimore area in Maryland originally. I'm a 4th-generation Baltimore Orioles fan, which in most previous years means I accept expressions of condolence But last year and this year have been pretty good, and they should go to the playoffs this year, which is really nice. And I'll probably fly back and go to a playoff game with my mom. I have 2 kids, one of which is leaving for college for the first time on Friday. The other one's a rising junior here in Boulder. We have 2 dogs. One of them is good and well-behaved and sweet, and the other is the other one of our dogs, and I will not tell you which is which. I am really happy living in Colorado, and I do lots of Colorado-y things for fun. On the right-hand side, have a research group that has postdocs and grad students and undergrads, and lately postbacks seem to be a thing as well. People who have finished their undergrad degree but are still transitioning to grad school, waiting a bit to apply. I really like teaching, and I teach in the astronomy department. It's astrophysical and planetary sciences at CU. That picture with me holding the sweater out is me explaining tides to students during a review session. I got snookered into being the department chair for 3 years. I've finished 1 year and have 2 left. That's why I'm wearing a sport coat. You will never see me wearing a sport coat, except maybe in that picture. And I'm trained by Fran, who took time off from this really big gas bag in the outer solar system, Jupiter, to train a student working on a super interesting planet, Mars. And it's the crowning achievement of my career that I convinced Fran to supervise a PhD thesis on Mars. I don't know how I snuck that one past her. And I use spacecraft observations. I'm trained with spacecraft observations, in situ observations of magnetic fields and charged particles. But lately, my research has gotten maybe an equal component of simulation and modeling within the group, because over the years, I first worked with many modelers, helping compare the data to their observations, then helping the modelers compare their simulations with each other. And then finally, some of the modeling started to migrate to my group. And the things we talk about today are the things that I like to think about scientifically. So I won't spend a lot of time there, other than saying I think my job is super, super cool. I like having teaching and research together and the synergy there. I can't believe people are willing to pay me to think about planets all day. And I also think it's super cool that these little tiny charged particles that you can't see and that you barely have any intuition for how they should behave can behave in ways that change sort of the evolutionary path of entire planets and influence habitability and things like that. That's really awesome. And I feel really lucky to get to think about things like that. So that's me, introductory wise. Okay, so the first thing I'll talk about is comparative solar system magnetospheres, except Fran just talked about that. So this will be a quick overview of comparative solar system magnetospheres, really 2 content slides, and then some pop quizzes for you. So off we go. First, an intrinsic magnetosphere. There are multiple kinds of magnetospheres. And so part of the community has started adopting the word intrinsic to describe one kind of magnetosphere, where the magnetic field from that planet is generated in the deep interior of the body through dynamo action. And dynamo action, you had, planetary and stellar dynamos, you had 2 lectures on those earlier in this summer school, so I won't go into that a lot, although I just gave a talk this past weekend on exoplanet magnetic fields, and as part of that talk, I had to spend some time talking about dynamos, and so I learned a ton, which was really fun. But when you look at the fluid equations for dynamos, there are lots of things that are important, lots of things that can make it complicated. And for rocky planets, especially, the details really matter on whether or not you get a dynamo in that object. For gas giants and ice giants, it seems fairly robust that they will often end up with interior generated dynamos. And 3 of the conditions that appear in the fluid equations that seem to be important on some level are the presence of some electrically conducting fluid and an equation of state that is conducive to dynamos, convection in the interior, and rotation of the planet. Doesn't have to be nearly as fast as you think. My understanding is that Venus's slow rotation is actually probably fine. Okay. That magnetic field generated in the interior provides magnetic pressure, B squared, proportional to B squared, and that pressure is sufficient to divert the incident wind, plasma wind, around the planet. If the planet is in the stellar wind or in the solar wind, then that B squared over 8 pi is balancing the rho V squared in the solar wind, the dynamic pressure in the solar wind, which is the dominant pressure term in the solar wind. And you get this really cool cartoon that Fran is responsible, Fran and her partner are responsible for introducing to the community of what the magnetosphere of what an intrinsic magnetosphere looks like. This is what I just said. I forgot that that was going to be on there. Okay. In contrast to intrinsic magnetospheres are induced magnetospheres. Some planetary bodies also supply magnetic pressure that can offset the rho V squared in the solar wind, even though they don't have a dynamo inside. They don't have an interior generated dynamo. And they do this through induction. And so that's why we call it an induced magnetosphere. And I can explain how this works. But the canonical case for an induced magnetosphere would be something like Venus. So the incident plasma, in this case the solar wind, has an entrained magnetic field, the IMF, interplanetary magnetic field. That interplanetary magnetic field is embedded in the solar wind, being carried by the solar wind, and so has some time-varying component. And that time-varying component is short compared to the diffusion time scale of that magnetic field into the planet's atmosphere. So it can be relatively steady as long as it's varying faster than the pretty long diffusion time scales into the atmosphere. In that case, Faraday's law comes into place. There's a dB dt here because it's time varying, and that dBt induces a current in whatever charge carriers there are in the planet. And for a planet like Venus, the upper atmosphere is being illuminated by the sun, including by the extreme ultraviolet light coming from the solar corona. And that EUV light is ionizing the upper atmosphere, creating the ionosphere. So there are abundant charge carriers in the upper layer of the planet's atmosphere. Those move in response to the time-varying magnetic field in the solar wind, and a current is created. That's the ionospheric example I gave you, but there are other places for there to be abundant current carriers. For example, a salty ocean is also a place where you could induce currents. Okay, next, once you've created a current in the ionosphere, then Ampere's law comes to play. Any wire that's carrying a current, like for these microphones up here or any of the power cords in the room, that's also generating a magnetic field that's circling around the wire. Super weak in the case of the wires here. But for the current in the ionosphere, the magnetic field that is generated is sufficient to deflect the solar wind around the planet. So this is how an induced magnetosphere works. There are lots of other details, lots of other physics, and the physics can be really cool. There are all sorts of interesting contrasts with intrinsic magnetospheres. One, for example, is that the orientation of the IMF determines the configuration of the magnetosphere. And the IMF is constantly changing orientations. So an induced magnetosphere is constantly kind of rotating around and flopping back and forth, in contrast to an intrinsic magnetosphere, where the magnetic field from Earth isn't changing its orientation. So the whole magnetosphere isn't completely reconfiguring all the time. Okay, that's intrinsic and induced. I think those are my only two content slides. So now it's your turn. Pop quiz. You have 4 minutes in your tables, working within your tables, to classify the objects below according to their magnetospheric type. Ready, set, go. We're fine. We'll found. One more minute. Okay. I see some tables are winding down in conversation. Others are off on related science topics. So before I reveal a couple of things, one, I just went and checked my answers with Fran to make sure she and I agree on everything. So, you know, putting things in a box, categorizing them correctly is not nearly so important as understanding each of the objects. Nevertheless, it's kind of fun to think about. So I want to ask you if there are any objects that you had particular trouble thinking about in terms of where you place them. I think there are 2 or 3 kind of tricky ones here, or challenging ones to think about. Enceladus. Yeah, so that's one that Fran and I talked about. What any others? Asteroid. Comet. Anything else? Maybe Pluto. Yeah. Pluto. Okay, great. So I'll give you what my answers are here, and then we can argue. That would be fine. So let's first start with the nones, because I didn't talk about none. I talked about intrinsic, I talked about induced. Intrinsic, a magnetic field generated inside the planet, although there's some gray areas there. Induced means there are enough current carriers on the planet to generate a planetary magnetic field on its own. None means there's nothing generated in the interior that's strong enough to really interact with the incident wind, and there are not sufficient current carriers to generate a field strong enough to interact with the wind. So the moon would be a classic example of really no magnetosphere. The solar wind just crashes in to the lunar surface. As a matter of fact, people talk about going to the lunar surface to try to reveal the history of the solar wind sometimes, which should be recorded in maybe the outer 10 centimeters or so of the lunar regolith. Asteroids could be magnetized, but we don't yet have any positive detections of asteroid magnetic fields. We keep putting magnetometers on spacecraft to asteroids, which is great. That is correct. And it's also the law that every spacecraft should have a magnetometer. It's a law I just now made up, but I also voted and it's been enacted. But we don't yet have direct evidence for a magnetic field at an asteroid. Yeah, big iron asteroid. It could be. I would imagine that Psyche is most likely to have remnant magnetization as opposed to active convection, but who knows? So the moon does have mini magnetospheres. I kind of ignored that here, but there are 4 objects in the solar system that we know of that have regions of the crust that are magnetized. Earth, but those regions of the crust are just dwarfed by Earth's global dynamo. Mars has significantly regions of the crust that are significantly magnetized, enough to interact with the solar wind on their own, which is why I put Mars in the intrinsic category in addition to the induced. It's not dynamo generated, but it's strong enough magnetization that's intrinsic to the planet that it is perturbing how the solar wind interacts with the object. Mercury, crustal magnetization was discovered there by MESSENGER, again embedded in a big global magnetic field, so it's unclear whether that really influences the interaction with the planet. And then finally the moon, which has really, really weak crustal magnetic fields. They're localized magnetospheres over portions of the crust. Those seem to be significant enough to either deflect incident solar wind particles slightly and or influence the motions of charged dust on the surface that are popped up off the surface by sputtering interactions with solar wind or micrometeorites. And that dust reconfigures itself, and you can see albedo swirls on the surface of the moon. At visible wavelengths, the places underneath the magnetized portions of the moon look kind of milky white compared to the surrounding black basaltic regolith. So moon, I wouldn't mark you wrong by marking intrinsic for the moon. Fran and I talked about Enceladus as well, whether it has an intrinsic magnetosphere and the jets. If you don't know much about Enceladus, it's an icy moon of Saturn that we believe has either a hemispheric or a global subsurface ocean, because we see that ocean being spit into space through cracks in the ice in the southern hemisphere. That geyser-like ejection of material interacts with the incoming plasma flow and at least creates alpha wings around the planet, if not a full induced magnetosphere. But Enceladus was one I wasn't super sure about. Comets, we don't have any evidence that any comets have an intrinsic magnetic field yet. They could, but we don't have any direct evidence. However, they are spitting out hydrogen and water in the coma. That's becoming ionized. And so comets, every comet that we know of that's in the inner part of its orbit has an induced magnetosphere. Yeah, good question. Maybe I should also put an X for none for comets. Yeah. Because when the atmosphere isn't actively being ionized by the sun, when the coma isn't super puffy, then it should be much more asteroid-like in its interaction. Okay, let's move on. Yeah, Harriet. Which object? Pluto. Fran, Pluto expert. I don't know why she makes fun of Mars for being so small when you also study Pluto.
Okay. I was very disappointed with Pluto. I thought it was very boring until we got there. And then it was just like, whoa. Okay, so Pluto has an atmosphere. Its atmosphere is quite extended because of weak gravity. It's a small object. And so we predicted, I wrote papers on predicting what the solar wind interaction would be like when we got there with New Horizons. And when we got there, we thought it would be huge, more like a big comet, big extensive induced magnetosphere. But when we got there, it turns out that it was much smaller, the interaction region. And that's because the atmosphere was not as extensive or as hot. And that's because aerosols are cooling out the upper atmosphere. And that's those aerosols are photochemical reactions of methane with the UV light makes the brown gooey stuff that makes haze in the atmosphere and then comes down and makes that brown gooey stuff on the surface. And so that made a much smaller interaction region. It's still escaping atmosphere, but it's not as much as we thought it would be. And so this is something to think about when you're going to such objects around the solar system. You really have to think about the chemistry of the atmosphere. You can't just say, oh, well, that's just atmospheric science. Who cares? It's chemistry, blah, 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 push it aside. It has effects on the escape of the atmosphere and what's going on. So Pluto's an interesting case. Yeah.
Thank you. All right, let's move on. Now some questions for you. Let's rather than small group discussion, let's just kind of take them one at a time collectively. Intrinsic magnetospheres are larger than induced magnetospheres relative to the size of the planetary body. Think about that for 10 seconds, and then we'll do show of hands. All right, your 10 seconds are up. Now you have to vote. So I'll give you three choices. The first one, who thinks it's true? Okay, hands down. Who thinks it's false? Okay, hands down. Thank you for playing along, by the way. I know this is like not what you were expecting today. Who thinks it is neither true nor false? I know. I pray I don't alter our deal any further. Okay. Okay, good. So in my opinion, it is generally true that intrinsic magnetospheres are larger than induced. The canonical pictures that we have for an induced magnetosphere, that's a small compact magnetosphere relative to the size of the object. The magnetic field that's generated in that interaction is relatively weak. And so the solar wind pressure can dominate much closer to the planet in a typical induced magnetosphere in comparison to an intrinsic magnetosphere where the magnetosphere is very large relative to the size of the object. So generally, this statement is true, but there are important exceptions, and this will become important later when we talk about exoplanets. So for example, cometary magnetospheres are induced, but the bow shock in a cometary magnetosphere is very, very far from the comet relative to the size of the comet. So in this limiting case where the atmosphere is incredibly robust, where the outflow is extreme, induced magnetospheres can be large also. Another example on the other side is an intrinsic magnetic field that is weak, or the lunar magnetic fields, for example, or even the Martian crustal fields if Mars didn't have an ionosphere in some way. Those weak fields can still stand off the solar wind, but they also lead to pretty compact magnetospheres. So intrinsic magnetospheres being larger than induced is not a hard and fast rule. It's more of a stereotype of intrinsic magnetospheres. Number two, Jupiter's magnetic field strength at the cloud tops of Jupiter is larger or smaller than Earth's surface field strength by a factor of what? So think about that for maybe 20 seconds, and you can discuss. Okay. All right. Come on back. I have indecision right now about whether to tell you what Jupiter's magnetic moment is compared to Earth's. I think I will not tell you what Jupiter's magnetic moment is compared to Earth's. So I'm only going to give you two choices. For the first one, larger or smaller. Who thinks the magnetic field strength at Jupiter's cloud tops is larger than Earth's surface field strength? Okay, who thinks smaller? Nice. Who didn't vote? Okay, you are correct. The magnetic field at Jupiter's cloud tops is larger than Earth's surface field strength. Jupiter's magnetic moment is 20,000 times larger than Earth's magnetic moment. Okay, four orders of magnitude larger. How much larger is the field strength at Jupiter's cloud tops than Earth's surface field strength? Anybody want to hazard a guess? Thousand. Let's use that as our baseline. Who thinks higher than 1,000? Larger, the factor is larger than 1,000. Who thinks smaller? Who didn't vote? Like all of you. None of you voted. Okay, so let's get some more ideas out. Why don't I just tell you the answer? It's about 8 times stronger, the field strength at Jupiter's cloud tops, which to me is very surprising. I would have guessed that it was much, much stronger than Earth's surface field, but factor of 8, same ballpark, and that's because fields fall off as 1/r², and Jupiter's a really big planet. So the cloud tops are much farther from where the dynamo is being generated than at Earth. Good question. What is the surface of Jupiter? So we'll often take the 1 bar pressure level in Jupiter's atmosphere as the surface level of Jupiter, and then also the top of the cloud deck, the part that you can actually see. And those two places aren't super far apart from each other. So it's approximately the same thing. Peter. Fran, what's he getting wrong there?
Right. Remember that the magnetosphere of Jupiter extends to 100 RJ upstream, right? So it's really big because of the strong field. And so, but more importantly, because there's no Dungy cycle, it's inside, it's all going around and around and around, all the way out to about 20 RJ. And so once you get stuff in there, it sort of accumulates and stays in there, so that, you know, the radiation belts are really big and strong because that stuff, there's nothing to remove them or perturb them. Whereas you think of the talks we've had already about radiation belts at Earth and how they varied. Lauren Blum showed some of this on the first day, how they vary with time because of the substorms and so on at Earth that disrupt the radiation belts. We don't have that disruption at Jupiter, so they hang around for a long time. Even though the surface field is not that much stronger than it is at Earth. Yeah.
Going the other way from Earth, I didn't do this calculation, but I imagine that the field strength at the surface of Mercury is much weaker than the field strength at Earth. The magnetic moment for Mercury's dynamo is smaller than Earth, and Mercury's a much smaller object than Earth. So the contrast there, it kind of goes the other direction. Okay, last question, and you have 0 seconds to think about this. A single object can change its magnetospheric type over time. Who thinks true? Who thinks false? Thank you for playing along. You are correct. Mars used to have a dynamo, used to have an intrinsic magnetic field. Today, it only has these crustal fields and mostly an induced interaction. Earth will someday lose its dynamo magnetic field. Any planet can transition between states. Okay. Now we're going to leave heliophysics for a while and touch on some topics that we think heliophysics can inform, and where the heliophysics community can be maybe more engaged in the next decade or something like that. So we'll do this kind of maybe with as much as half of my time today spread over the 3 lectures is not actually talk about heliophysics, but talk about things that heliophysics can inform or be informed by. So let's do some comparative atmospheres, solar system atmospheres. We'll do bulk atmospheres right now. So another question, how many of the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Wait, did I count right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many of the 10 objects in that picture possess an atmosphere? Okay, I heard 8. Do I hear other numbers? Sure. Okay, I heard a 10. The question was, do I count exospheres? And I said, sure. I hear an 8, I hear a 10. Okay. Nick. I will. And that was what this slide was designed to get us into. Yes. No, you're fine. No, that's great. So the answer to this question, there's no hard and fast answer to this question. At least 8 of the objects in this image have what we would call an atmosphere, and there are more objects in the solar system that have atmospheres than are shown here. And by atmosphere, I mean a collisional atmosphere, where collisions are happening regularly in the gas that's gravitationally bound to the planet. 2 of the objects in the picture, Mercury and the Moon, have what are called surface-bound exospheres. So there is gas that is gravitationally bound to the planet, but it is so rare, the density is so low, that collisions are very unlikely. You can treat each one of those particles as if they are on a completely ballistic trajectory, from the surface up and then all the way back down to the surface again. Collisions do happen, but you can ignore them when you are putting together a physical model to describe what happens in that atmosphere. They are so unimportant. So 8 or 10 is fine. Io has a collisional atmosphere. Europa has a collisional atmosphere. Very, very thin compared to even Mars's thin atmosphere, but there are other objects as well. Yeah, what's that? Pluto, yeah, which was in the object, has collisional atmosphere, although Pluto's atmospheric state probably changes quite a bit, or the atmospheric characteristics change a bit over its highly eccentric orbit. People talk about the atmosphere freezing out onto the surface when it gets farther from the sun. Yeah. So there are a variety of ways to do this even before New Horizons, but the main are ground-based telescope observations. So you can look at occultations of Pluto. So some star is passing behind Pluto from your perspective, and you can see how the starlight is dimmed as it gets closer and closer to the surface of the planet, to the limb of the planet from your perspective. And you can use that to back out that the atmosphere must be getting thicker, 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 and then back out that it must be collisional from there. Okay, so we can classify atmospheres in the same way we classify magnetospheres. Again, the classifications are only mildly important. What's important is understanding each object and the physics that govern it. But loosely speaking, there are these major terrestrial planet atmospheres, Venus, Earth, and Mars. And I'll include Titan in this as well. The surface pressure on Titan is 1.5 bars, 50% higher than Earth's surface pressure. And it's a nitrogen atmosphere. The giant planet atmospheres, including the ice giants, so Jupiter, Saturn, Uranus, and Neptune. There are these really thin atmospheres, but they're still collisional, and they're listed up here. Cometary atmospheres as well, which are robust, but change over the orbit of the comet. And then surface-bound exospheres, you can still describe what's happening in those exospheres using material that you would learn in an atmospheres course. You learn about exospheres when you're studying Earth's atmosphere or the atmosphere of Venus or Mars. And it's the same physics that's happening on the moon or Mercury. It's just an exosphere. Collisions are rare. Okay, another distinction to make here in classifying atmospheres are primary or primordial atmospheres versus secondary atmospheres. And this gets back to how we think the solar system formed and evolved. We think that based on the composition of our sun, which is 98% hydrogen and helium, we think that the disk from which the planets formed was also 98% hydrogen and helium. The planets condensed out of the stuff that wasn't hydrogen and helium, and you made rocky planets and giant planets. And those planetesimals, once they were forming and turning into planets, were able to attract the gas from the disk, from the solar nebula. And the gas that they attracted was, guess what? 98% hydrogen and helium, because that's what was there. The atmosphere of Jupiter today is 98% hydrogen and helium. Saturn, pretty close as well. So Jupiter and Saturn have primary or primordial atmospheres. We have every reason to believe that Earth and Mars and Venus and Mercury and even the moon also had a primordial atmosphere too after they first formed, that they gravitationally attracted hydrogen and helium predominantly from the solar nebula. That's not the atmosphere we have today. So that hydrogen and helium and all the other trace gases that were there are gone. And that's where atmospheric escape or atmospheric blow-off becomes important. The early conditions in the solar system were not so friendly for these primordial atmospheres, especially on low mass planets, where it was quite easy to strip those really low mass species away out of the gravitational field of the planet. Okay, it was also super hot early on in the history of the solar system. So Earth, Mars, Venus lost their hydrogen helium atmosphere. And what we're left with, what we are embedded in right now as we talk to each other, is called a secondary atmosphere. These atmospheres are formed primarily by outgassing from the interior. And I've been teaching this all wrong, I found out within the last 6 months. I thought that most of this was just coming from volcanoes and populating the atmosphere. And that is true. Outgassing from volcanoes does add to the atmosphere. But it turns out a whole lot actually came while the planet's crust hadn't even solidified yet. You know, this magma ocean on the outside of the planet has a lot of gas that's dissolved in that melt. And that magma ocean overturn actually kind of releases a lot of gas before the volcanoes have even formed. Yeah, Lika. Yeah, I can give a range, but it's almost certainly too large, the range that I would give. I think it's in the first 100 million years, but it's probably less than that even, which is scary to me as a planetary scientist, where we have the geologic record on Mars goes back to maybe 4.1 billion years ago. I like to think of that as my starting point. It really makes me sad that I have to start thinking back earlier than that to times when we really have no evidence of what things were like. You can also get delivery of atmosphere from comets and asteroids as well. And there's a debate. It's not much of a debate anymore, but there's discussion about where Earth's water came from and the isotope signatures in Earth's water and whether they match the material we expected in the inner solar system at that time, or better matches comets that were in the distant solar system. And then subsequent atmospheric chemistry has evolved the atmosphere as well. Okay. So for a lot of the rest of the time, with apologies to Fran, I'm going to talk about rocky planet atmospheres. And so here's, Fran just fell asleep in her chair. Mercury, Venus, Earth, Moon, and Mars. The Moon is a planet for the sake of this discussion. planetary scientists study the moon, has all the same processes that we think happen on planets. So these are the 5 terrestrial worlds, maybe is a better thing to say. And specifically the ones with robust atmospheres, Venus, Earth, and Mars. There'll be a lot of focus there. To scale, here's what an ice giant would look like. Not nearly as big as the mental image that I held in my head for a really long time. So Uranus and Neptune are kind of in this regime that exoplanet scientists call super Earths, you know, sort of 1.5 to 4 times the size of Earth. Not nearly as big as I always thought. And then Jupiter as well, much, much bigger. Okay. This is not going to be discussion. This is more just you think as we reveal this table line by line, in part because I find tables incredibly boring to present, really informative for the person who put it together, really boring for the person who didn't, that is trying to look at it for the first time. So we're going to look at it together in this way. Let's compare the surface temperatures of Venus, Earth, and Mars. Take a guess about what the surface temperature of Venus is and what the surface temperature of Mars is, just in your brain. Okay, Earth, 288 Kelvin. The average global surface temperature on Earth is 15 degrees above the freezing point of water. Okay, that's really critical. For Earth, without greenhouse gases in our atmosphere, the average global temperature of Earth would be 15 degrees below the freezing point of water. So greenhouse warming in Earth's atmosphere has actually facilitated the fact that we are all alive here and able to have this conversation. Okay, Venus, incredibly hot. Mars, the average global temperature is, you know, 55 degrees below freezing. But there are places on Mars that near the equator on warm summer days that get up above the freezing point of water. Surface pressure, I forgot to ask you to think. Earth's surface pressure is 1 bar because scientists are lazy. You know, what's the pressure at the surface of Earth? It's 1 bar. I just made that up because I was eating candy at the time. I don't know how that came about. But Venus surface pressure, 2 orders of magnitude larger, around 100 bars. Mars surface pressure, 2 orders of magnitude smaller, around 10 millibars. Okay, so they're 2 orders of magnitude either way.
I've got a quick question about that temperature of the surface of Venus. It's hot.
Yes.
I usually, when I give talks or classes, I've said this is equivalent to the cleaning cycle in your oven, but I don't actually know. Does anybody know? Is that what is it? What is that temperature? 740 Kelvin is really hot. Do we have an analogy? Anybody know?
I don't have a good one.
Curious. What do you think about?
Other than really hot.
Well, I mean, I'm
Yeah.
just thinking if you're trying to put instruments on the surface of Mars,
Yeah.
you know, you've got a problem. I mean, the Soviet Union had a lander that was there for about an hour and took some really cool pictures, but that was it. Then it died.
And it was mostly the temperature, not the pressure for those
Yeah.
instruments.
Oh, really? You think that's what it is? Okay. Yeah. Nasty, really nasty.
All right, I'm going to speed it up a little bit here. Composition. You know what the main gas is in Earth's atmosphere, Venus atmosphere, and Mars atmosphere? Okay, Mars and Venus are the same, 95% CO2. Second most abundant gas is nitrogen in both atmospheres, because that's what comes out of volcanoes in the interior of planets. Okay, Earth, not the same. 78% nitrogen, 21% oxygen. Turns out the third most abundant species in all 3 atmospheres is argon. And so Earth is the oddball here, and we can come back and talk about why that is in a bit. Yeah. Okay, yeah, let's talk about it right here, at least a little bit. So I want to argue that Earth's atmosphere is the same composition as Venus and Mars. But it turns out that CO2 dissolves in water, in liquid water, and combines with minerals in that water to form carbonates. And those carbonates are currently at the bottom of our oceans. And they get recycled by plate tectonics and get re-emitted through volcanoes. But a homework question that Fran and I have each given students before is add up all the CO2 and the carbonates at the bottom of Earth's oceans, pretend it was back in the atmosphere. What atmospheric pressure do you get? Turns out around 100 bars. Okay. So Earth has the same atmospheric composition as Venus. It's just hiding at the bottom of the oceans right now, the CO2. Okay, water content, which is the wettest atmosphere, which is the driest. Think about it, think about it, think about it. I didn't give you enough time. Here it is. Okay, Earth, parts per million, very, very wet, compared to Mars and Venus, both of which are dry. Venus is bone dry, and heliophysics processes are responsible for that. We're fairly certain. Okay. Okay, under the surface, different from the atmosphere. So not necessarily inconsistent. And all three of these objects, we think, have as much as 10 oceans of water trapped in the interior. Whether that water is accessible to the surface is a totally different story. Precipitation, where does it rain and snow? Turns out all three, but Venus, that precipitation doesn't reach the surface. The sulfur dioxide in the clouds of Venus, we do think precipitates, or at least it's possible that it does form acid rain, but it's so hot that it never reaches the surface. It all evaporates again before it ever gets there. Earth, you know about precipitation here. You've experienced it in the last 2 weeks, and Mars does have frost that will condense out and maybe even flakes of snow in the polar regions. Circulation and winds I loop together, and I'm going way too slow, so we're going to go through this last part. I'm not going to talk about atmospheric circulation because it doesn't really touch on other parts of what I'm presenting today, but you may have had a class or at least seen diagrams showing that Earth has circulation cells that are organized by latitude. Air rises at the equator and then sinks again at mid-latitudes, and there are 3 circulation cells for Earth. Jupiter has 7 circulation cells on each side of the equator, and that's why you see the stripes on Jupiter. Mars and Venus each have 1 cell, basically 1 circulation. Mars, sometimes it doesn't even rise at the equator. There's 1 global circulation that stretches from one pole, maybe 2/3 of the way to the other pole and back again. So very different circulations. And this is a combination of planetary size and planetary rotation. Winds, and then seasonal variation. Venus, nothing. There's no, Venus is Venus is Venus in terms of seasonal variation. Mars has the most extreme seasons of any of the 3 planets, even though it has the same tilt as Earth. And we know that the tilt of the planet is what causes the seasons. It turns out Mars also has an eccentric enough orbit that gives an extra kick to the seasons. So southern summer on Mars is the hot summer, and northern summer on Mars is the not as hot summer. And by hot, I actually mean cold, because Mars is cold. But you know, southern summer is more extreme. When we get dust storms on Mars, they're always initiated during southern summer. Okay, that's what they look like. Hopefully I brought that table to life a little bit in contrasting these 3 planets. Now let's move on to thinking about the atmospheres and how they evolve in time. How long do I go to 11:30? Okay. I thought I was going to be presenting from my own laptop, and so I have the ability to type on this slide. but we'll just do it kind of out loud. How about you have 3 minutes in your tables to come up with 4 ways to change a planet's climate. They have to be fundamentally different. Ready, go. Okay. I was 3 minutes and 40 seconds. Close enough. But what I will do is ask each table for just one answer that they talked about. And let's see how it goes. Now I can see panic in eyes. Like, oh, okay, look quick, come up with one. So now I'll give you another 30 seconds or so. Okay, that was 30 seconds. And by that, I mean, that was 20 seconds. I'm calling on tables at random too. So what'd you come up with? Human activity, biological activity. Great. One, let's go table. Okay, evil superhero mode. You are like tugging the planet somewhere else. Nice, good. Change its magnetic field. Heliophysics comes into the mix. We're going to talk about this later today. Nice. What's that? Tilt angle. Okay, tilt it more, tilt it less. Okay, let's go here. I've forgotten which tables I pointed out. So those 2 tables next. Yeah. Okay, that's like even more evil superhero. You're like, you're gonna crash stuff into it. Okie dokie, good. Here. That's fine. Ooh, deflection. Yeah, the planet thought something was going to happen to it, but you messed with the star instead. What did you mess with? Okay, so the stars change activity level in some way. Okay. We didn't go to your table. This is the final one. Nice, big mirror. So people write papers about this. They have written papers about this in terms of terraforming Mars. Chris McKay has written a paper about this. He was a former grad student at CU, and he's at NASA Ames now, and you can pretty much just see him on the Discovery Channel like almost every day. He's often like, I don't know what I think he has a super cool job. He just like travels around the world and picks up ocean water or looks under rocks and kind of ties planetary science and astrobiology and geology all together. And he's written papers about giant mirrors terraforming Mars. So these are all potentially theoretically possible ideas. I wouldn't advise some of them in terms of expense, effort, and ethics for some, but you have a general idea. Another thing you could do is disintegrate Earth's moon. That would change our climate quite a bit. Earth's moon provides a stabilizing influence on our tilt. So there are all sorts of out-of-the-box ideas here. But I'm going to argue that everything you just said, those things can be categorized as one of four things, each of them. So here are the four. And this comes from sort of basic equations for surface temperature of the planet. I'm going to use surface temperature as a proxy for climate altogether. And so one, I think you've seen in this summer school maybe, which is global energy balance. Is that true, Farzad? Or yeah, okay. Global energy balance is on the left. The amount of energy coming from the star into the planet, encountering the planet, is on the left, where S is the intensity of the emitted power at the location of the planet. D is the distance of the planet from the star. A is the albedo or reflectivity of the planet. And R sub P is the radius of the planet. Okay, that's the amount of energy encountering the planet. And on the right side is the amount of energy that the planet is giving away. And this is energy emitted at the surface of the planet. It's proportional to the temperature of the planet raised to the fourth power. We'll come back to temperature, times the surface area of the planet, 4 pi r squared. If you look at this balance, you'll notice that the size of the planet doesn't matter, cancels out. Okay, in this limiting case where we have assumed that the planet isn't changing temperature. Okay, the energy in, energy out, power in, power out, those are balanced. Okay. On the right-hand side, now we're being careful about the temperature. The T effective is the temperature at which the planet is emitting away to space. But that isn't the same as the surface temperature. And that's because there are gases that absorb and re-emit infrared radiation between the surface and space for many planets. So you can do some radiative transfer, and the simplest thing you can do is divide your atmosphere into horizontal layers. So it's a 1D plane parallel gray, which means wavelength doesn't matter, atmosphere. So when I teach this to undergrads, I call it the pancake model of the atmosphere, where each layer absorbs energy from the layer above it and below it, and it emits energy that only goes into the layer above and below. So you can do this, and you find out that the surface temperature is related to the effective temperature through this tau, and tau is the optical depth of the atmosphere. Essentially, how many pancakes did you have in your model? Okay, so there are things there. There's tau, there is albedo, there is S, the amount of energy coming from the star, and there's D, the orbital distance. These are the things that matter. And broadly classified, that's the solar output, the planetary albedo, the greenhouse gas content, which is tau, and the planetary orbital elements, which have been simplified here to D, but things like tilt and eccentricity also matter. So I think these are the 4 ways to change climate. So you can make the star variable, or you can have the star get brighter over time, or the EUV output of the star decrease over time. The planet itself can form more ice, it can form continents, and its albedo will change. It's outgassing, and it's also subjected to impacts, which might be stripping gas away. The greenhouse gas content can be changing. And then the planet can rock back and forth and move in and out. You can tug at places. So hopefully every answer that you just gave, you found a way to put it into this framework of 4 things. All of these things change with time. So studying planetary climate is hard and super fun for people who do that. I'm not claiming that I do. I think about one very small piece of that that's heliophysics related, the atmospheric escape piece. But all this stuff changes with time. It's a complicated system. I'll give 2 examples. Solar output, you may have seen this earlier in the last week and a half, I don't know. But this is based on a sun in time program. So observations of G-type stars like our sun of different ages, and then figuring out what their total luminosity is. And we've known for a long time about the faint young sun. And so here is today at 4.5 billion years ago. 4 billion years ago or so, the sun was 30% fainter than it is today. It's getting brighter and brighter and brighter over time in terms of the total energy being emitted by the sun. Okay, so solar output is changing. That has implications for climate, and it creates a paradox, not a paradox, a pop quiz or a puzzle for people studying Earth, which has had a stable climate for billions of years, even though the solar output is increasing. And that's because there are negative feedbacks in Earth's climate system that keep the climate relatively stable. Okay, another example would be the orbital elements. We can compute, going back in time, what the tilt of Mars should have been, and the eccentricity of its orbit, and the argument of periapsis. And we can use all of those things to compute the insolation, the amount of energy Mars should be receiving. And we find that even though Mars today has a 25-degree tilt compared to Earth's 23.5-degree tilt, that the inclination of Mars varies between nearly 0 degrees and something like 60 degrees. And that has huge implications for the size of the polar caps on Mars, which in turn has implications for how much gas can be in the atmosphere, how energy is exchanged, and the climate of the planet. We can calculate this back around 200 million years before the error bars get too large for us to really know what happened. My understanding is that our uncertainty in the orbit of the asteroid series is what limits our ability to calculate this. If we had more sig figs in our determination of the orbit of Ceres, this plot could go beyond 200 million years ago. But Mars wobbles back and forth because it doesn't have a big moon to keep its tilt stable. No, Mars is interacting gravitationally with everything else in the solar system. Some things are more important, some are less. When you go back beyond 200 million years ago, it's either Ceres or Vesta. I can't remember which one. That becomes a limiting factor, our uncertainty there. Yeah. Okay, atmospheric source and loss processes. I'm aware of the time, so 6 minutes or so. A lot, 10 minutes or so, great. A lot of the rest of today will be, we'll at least have atmospheric escape in the back of our minds. But when we talk about adding or removing greenhouse gases, atmospheric escape isn't the only part of the picture. So I had a really horrible PowerPoint diagram that I made showing all of the escape and source processes. And I showed it in a class one time, and I had a student who was a double major in graphic design. And I made some throwaway joke in the class, like, this is really horrible because I'm horrible at PowerPoint. I wish I had a better one. And she came to me the next week with this. So now I always just show this and think about her every time I show it. It's really cool. So this has all the processes that I would think of in terms of adding and removing gases from an atmosphere. And it's a lot to look at once, so let's just look at it a little bit at a time. So there are processes that exchange gas with the surface. Some are reversible, like phase changes. You can sublime polar caps, you can condense onto polar caps, fine. Some of them are essentially irreversible. Mars is red because the surface oxidized, a chemical reaction. Oxygen in the atmosphere reacted with iron in the Martian crust, maybe in the presence of liquid water, so rusting like on Earth, but you can also get oxidation in the absence of liquid water. So that's kind of an irreversible process that removed oxygen from the Martian atmosphere. You can trap gas in the near subsurface. It can like stick to the surface layer. You can dissolve it in liquids, and you can outgas. Yeah. So this will come back this afternoon, but I always try to answer a question in place if I can. And so when I came into graduate school 30 years ago, the canonical wisdom was that magnetic fields prevent escape from happening, that Earth has a thick atmosphere today because a magnetic field protected it. Mars doesn't have one today because it doesn't have a magnetic field. The community has been greatly questioning this for the last 8 or 10 years. Some people now actually think that the presence of a magnetic field leads to more atmospheric escape than if the planet didn't have one. So there are all sorts of factors that can influence the effectiveness of these processes. Magnetic field is one potential one. Rotation rate might be another one in the planet. The planet's size might be important. So I would think of magnetic field as a cofactor as opposed to a process here. Okay, escape processes we'll talk about this afternoon, but I identify 5 escape processes in what I'm doing. Some people identify 10. Peter? Yes, but in that case, I would say the process is wave-driven particle acceleration, and magnetic field is something that influences that process. Yeah. And then finally, impacts. And impacts can deliver volatiles to a planet, deliver gases. Comets are just a big ball of gas waiting to happen. If it lands on a planet and is heated up, then all those ices can be released into the atmosphere. But impacts can also strip atmosphere away. So in some part of my research program, I have a student thinking about this problem, but we won't talk about it further today. Okay, I'm going to skip this interlude because we can go through this interlude when we talk about atmospheric escape, but I want to spend our last 5 minutes talking about evidence for change on the planets. Okay, so this is like a 3-slide interlude. Pretend you didn't see these. Okay, great. Unfortunately, that's what I just missed was maybe the most heliophysics-y of this last part of the lecture, so I'll sneak it in this afternoon. Great, diffusive separation probably, hopefully. But I can mention it briefly later today. So I think there are just 4 slides left. So let's briefly go through evidence for climate change on each of these planets. And a lot of these topics today that we've been talking about and all week that you've been hearing about, each one of them alone is probably, a 2-hour lecture. Could be a 2-hour lecture. This is certainly one of those slides, evidence for climate change on Mars. So it's almost painful to me to reduce it to just this. But we have 3 classes of evidence that tell us that the climate on Mars changed. One is geomorphology. We see riverbeds on Mars with no water flowing in them now. And we know that there's an atmosphere on Mars that's too thin and too cold for water to be stable as a liquid for the periods of time necessary to carve these. So you can just look at the shape of the surface and infer that the atmosphere used to be a happier place for water as a liquid. Okay, so one image, you know that the whole planet's atmosphere must have changed. Also, we can send spacecraft there, which with spectrometers, and they can look at the surface at various wavelengths and tell you what the surface is made out of, what minerals are present. So that's geochemistry. In this image right here, the colors that you see are phyllosilicates. Phyllo, love, silicate, silicon, love, silicate. But a phyllosilicate, another term for phyllosilicate is clay. So clays on Earth form in the presence of liquid water. Can't happen today on Mars. And finally, isotopes. This is why we had the interlude that I skipped. The isotope ratios of certain species in the atmosphere show that planetary atmospheres are enriched in the heavy isotope. So for now, please just accept that when an atmosphere is enriched in a heavy isotope, that's a smoking gun signature that atmospheric escape has been effective on evolutionary timescales for that planet. Venus, again, isotopes, D to H, those are isotopes. And the
Dave,
yeah,
the previous slide,
yeah,
evidence on Mars. All of these methods show the atmosphere changed 3.5 billion years ago, right?
it changed somewhere between 3.8 billion years ago and today. And the surface features especially allow you to put some constraints on when that happened. So most of the atmospheric change should have been done by around 3 billion years ago.
3 billion years ago.
Mm-hmm.
And what was the most sophisticated life on Earth 3 billion years ago?
Bacteria.
Slime mold. Yeah, right.
Okay.
Yeah.
Point made.
Yeah.
Okay. Yeah. When the general public hears about scientists' excitement about life on Mars, they think little green people running around on the surface. But the scientists,
Megafauna, charismatic megafauna.
yeah, giraffes with 3 tails and things like that. But what scientists are really excited about is finding evidence of even single-celled life. That would be super exciting for the scientists. Fran is very worried that when the general public finds out, they're going to be so disappointed.
Well, I just don't think we should be spending, oh, never mind.
Okay. I think we have our lunchtime topic. Okay. Venus, I promise, Nick, I only have a couple left here. D to H in Venus atmosphere compared to D to H at Earth is much higher, which means Venus atmosphere is even more enriched in the heavy isotope. Atmospheric escape has been even more important there than it has at Earth. However, we don't have a lot of other evidence for change, no geologic evidence for change. The number of impact craters on Venus is pretty small, and this suggests that the entire surface of the planet has been resurfaced. The whole planet has been resurfaced within the last 500 million years. And the debate among the Venus community is whether that all happened at once 500 million years ago, and then the surface has been collecting craters, or it's happened piece by piece over the last 500 million years and is even continuing today. Earth, and then one more after this. There's lots of evidence for climate change on Earth on lots of different time scales. I won't go through each of these one by one because we're running out of time. But I'm sure you've heard of most of these, if not all of them. Ice cores, using trees, and then using geology as well, sediments. And so by coupling these records on different timescales together, we can get a rough idea of how Earth's climate has changed over time. Certainly a more robust idea than we can get for any other planet in the solar system. And of course, the uncertainties grow as you go back in time. I'm going to skip this one too, because we already talked a little bit about CO2, because there's just one after this. We can come back to that. So this is kind of the idea I want to leave you with for the terrestrial planets, is that if we understand solar system formation appropriately, then Venus, Earth, and Mars all should have started roughly the same. There could be differences in minor differences in chemical composition that can be important for dynamo formation, for example, or the iron content of Mars's crust. But to 0th order, the planets should have started the same. They should have lost their primary atmosphere and developed a thick CO2 secondary atmosphere. And then Venus, Earth, and Mars have diverged since then. Because Venus is closer to the sun, any water on the surface was more likely to evaporate, more likely to dissociate and break apart, and hydrogen is relatively easy to remove from an atmosphere, which is why we think Venus is so dry. Mars, far enough from the sun that, and cold enough that maybe a lot of that early thick atmosphere was lost to the surface and subsurface, and or escaped to space, a combination of the two at Mars. And that's what put them on their paths to today, along with a lot of other things like plate tectonics. Earth has it, Venus and Mars, as far as we know, do not. To what extent did the atmosphere play a role in that? And to what extent did atmospheric escape of atmospheric particles and dehydration of atmospheres play a role in whether or not a planet has plate tectonics? So it's all kind of tied together. The geology, the heliophysics, the atmospheric science all go together in telling us what happened to the climate. So I think that's it. I could advance and find out, but I'm just going to pretend this was my last. No, I have to advance. I have to find out. That was it for that. Okay. Close enough, Nick? Okay.
Got a question for you, Dave. Water delivery to the planets, formation. When I teach solar system formation, I always make a point about migration of Uranus and Neptune, and Uranus and Neptune then scattering the Kuiper belts and presumably sending icy objects into the inner solar system. And I've always assumed that's where our ocean came from. And the water, you know, so there would there be a difference in terms of Earth, Venus, and Mars in terms of water delivery? Or do we guess that they probably would get the same amount of water that way? Or, you know, you mentioned, was it 10 oceans or 20 oceans or some number of oceans of water inside the terrestrial planets? And whether that came from mixing up of the disk, bringing in some ice, or whether it was stuff coming during the migration of Uranus and Neptune. I guess there's no way, I don't think there's any way of telling. Is there a way of telling?
I'm certainly not an expert enough to know if there's a way of telling. I think when I was in grad school, a lot of people thought that our water was delivered by comets after, you know, Earth's surface solidified, and the water was delivered later because it was too warm in the inner solar system for water to be anything but a gas. But I think having so much water deep inside the planet, I'm not sure how we know that or how we think we know that. That to me suggests that a lot of the water that Earth has was incorporated while it was forming, before it solidified. So it should have been from the disk material. And we know from studying exoplanet solar systems that migration was a lot more important can be a lot more important in solar system formation than we originally thought. So now I think there are a fair number of people who think that a lot or most of Earth's water was incorporated as the planet formed, and maybe not not delivered later, so much of it.
So the disk could have been a lot more more messy, more non-uniform. It could have had, it wasn't just layers of rock, metal, then rock, then
Ice,
you know, ice. It was much more mixed up.
Yeah, it was,
Yeah.
the
Yeah.
disk was much more turbulent, and there was a lot
Right.
of inward and outward migration of material.
Right. Okay.
So,
Makes sense. Things are more messy. Isn't that invariably what we see, whatever object we look at in the universe? The closer you look, the more messy it gets. I mean,
Questions for David or Fran? Oh, we'll start over here.
I have a question. I have a question for Fran. You mentioned that the moon has crustal magnetic fields on the surface. So is that from the interaction with the Earth's magnetosphere, or is it from its own intrinsic magnetic field that disappeared a long time ago? And how do we know?
the moon.
Yes.
Right. My understanding is that the core of the moon is sufficiently small. And also, if the moon formed through impacting with the Earth, and maybe in that process delivered some of its iron to the Earth and made the Earth's core bigger, perhaps, but also meant that the core of the moon is very small, which it is, we know that, and almost certainly never had a dynamo. And so that remnant magnetization of the surface, I think, has to be the lava, when it froze out or cooled off and froze, had remnant magnetization from the interplanetary magnetic field going by. That's my understanding. Do you have any different view of?
there's one cartoon physicsy explanation, but no detailed models. And so I think Fran's answer is very plausible. The hand wavy cartoon physics explanation just sounds really strange to me, but that explanation is from Lon Hood, actually, who said that, okay, the crust of the moon formed, then it received impacts, and sufficiently large impact on one side of the moon sends shock waves and heating all the way through the crust of the moon, and it ends up converging at the antipode to the impact site. So you get additional heating there, so much heating that you can melt the rock above its Curie temperature. And when you do that, then the rock can be magnetized if there's any ambient magnetic field there. And then he further argues that the plasma that is traveling around the moon in all directions is carrying magnetic field, and that magnetic field also gets amplified at the antipode site and is recorded. And this explanation comes from a possibly very coincidental observation that many of the lunar magnetic anomalies are antipodal to large impact basins.
Okay.
Yeah.
So yes, for calculating the standoff distance of the magnetopause, so there was like this magnetic field that got like disturbed, and then currents inferring from that. Do we know where the 2-factor comes from, or is it just a guess?
The 2-factor comes from that current. Actually, I showed at the very beginning of that derivation a theory from 1930s or something, where it had the vertical, had a current, had internal magnetic field, had the pressure coming in, and that factor of 2 comes from the fact that the pressure of the solar wind interacting with the magnetic field inside, you end up producing this current which doubles the effect of the dynamo inside. Okay, so you can think of that doubling the effect of the dynamo inside. Okay, and then that's why you end up with that factor of 2. But it's a bit of a fudge factor, to be really honest with you, right? Yeah.
So I guess a question for either of you. I was interested in the sort of argument about how Earth has a similar atmosphere in the end. It's just the CO2 is locked away. Does that argument work for somewhere like Titan, or is there something fundamentally different going on there which gives it a big nitrogen atmosphere?
Whoa, that's a good question. I completely dismissed thinking about Titan until a couple of weeks ago, and someone reminded me, and I started thinking about it some more. I don't know what the story is with Titan. Titan is so far out in the solar system, right? It's a lot colder out there. And so you've got liquid methane in those lakes. And so you don't get liquid methane on the surface of even Mars, I don't think, right? It's not cold enough.
no.
And so that makes a big difference in terms of once you start putting ice, which has got methane and then liquid methane, and then you've got nitrogen, but nitrogen's not frozen. Nitrogen is gaseous. Now you move out to Pluto and the nitrogen becomes frozen, right? So as you move out through the outer solar system, you end up with very different atmospheres, and it's largely due to temperature. And you get different gases in different situations like that. So I would love to hear from an astrobiologist about potential life on Titan, just because I've been hearing about methane bacteria on Earth, and there must have been methane bacteria in Titan at some point. Maybe not. Who knows? But pay attention to that, because we're sending a helicopter. Dragonfly is going to go to Titan and fly around and measure stuff. Maybe looking for, I don't know how they look for life, but anyway, that's an important question. But it's a bit down the street. We've been focusing on Mars and Europa and things that we've been getting data from. But down the road, think about Titan. Could be interesting.
And I probably would have gone to the same answer too, but it still leaves me with a question. I mean, it's much colder there, so the chemistry is going to be different. And Titan has a whole nitrogen cycle, and it has a whole methane cycle. And so the nitrogen and the carbon, I think, are accounted for. But the question I'm left with is, where is the oxygen? I mean, because Titan
Right.
should have formed with
Yeah.
CO2.
So I had a
So I don't
talk
know
by
what it is.
Francis Nimmo, who's a geophysicist. He was talking about there could well be a liquid water ocean deep underneath, and he's really talking liquid water ocean, not this new discovery at Mars, which just says that rocks have got water in them in order to explain the viscosity of the rocks deeper down, right? Which is the new, it's been in all the newspapers the past week about this discovery of water in the rocks deep down on Mars from the seismology, right? But what they're talking about at Titan would actually be an ocean. Underneath all of that Titan ice, whether or not it might be an ocean that could have bare life, who knows? It may be way too deep and too cold and too high pressure and detached. All cool things.
Hi, I was thinking about where the aurora would form as the Earth's dipole flips. And I was wondering for something for a planet like Uranus, where the magnetic dipole is off axis, its rotational axis. Do you know if there's how magnetic reconnection occurs on the day side, or if there's magnetotail loading, or what all happens with that?
Great questions. So first of all, the idea of what would happen to the aurora during an Earth flip, it probably goes all over the place, gets completely messy all over the place. And I'm hoping that you're going to show some aurora at Mars to give an example of a complex field.
How long is lunch? Yes.
Yeah, right.
Yes.
Anyway,
Sure.
Maven is finding the
Totally
group
in
at
the fun.
CU, the Maven team at CU, the IUVS team is finding all sorts of aurora on Mars associated with the crustal magnetic fields and the interaction producing aurora. And I would imagine the same sort of thing would have happened at Earth during the dipole when it was flipping, and you were getting these very high order multipoles producing this much more structured, weaker field, probably somewhat like the Mars field. Okay, But Uranus is another question. Okay, so there have been some detection of aurora at Uranus, the Voyager flyby. They saw it sort of around the polar region, sort of the dipolar region, they saw some emission around there. And there is some claim of Hubble seeing aurora. I was a reviewer of that paper and I said yes, because I wanted to support the idea of going back to Uranus. So even though I had some doubts, I thought, well, let's just push it, it'll be fine, Now I have more doubts about it, and it would be, we need better evidence. And, I don't think JW is going to help, but you need a big telescope. I mean, Uranus and Neptune are far away, so it's hard. But indeed, you think about a offset tilted dipole, or some high multipole, and you've got the solar wind interacting, whether you call it a Dungy cycle, whether you call it some kind of complicated interaction between this. I mean, it's messy, really messy, and the models show that. Then yes, I would guess that you're going to get some pretty interesting dynamic aurora, highly structured, highly variable, which would be really cool. So yes, we should definitely carry a UV instrument to look for aurora on Uranus when we go there. Well, when you guys go there, I'll be probably.
And did you talk about how a reversal happens? What happens to the field during a reversal?
We showed
earlier
the
this week?
movie of the Earth. There's one of the Earth where it showed it went from pointing one way with the North Pole and the South Pole, different colors, then going all variable all over the place, high order multipoles developing, and then growing in the other direction. Yeah. So we showed
Yeah,
that.
so it doesn't just.
It
do-
doesn't.
It
No,
doesn't do
definitely
this.
doesn't do that.
It does like
Yeah, there you are. See,
that.
that's it. That's his dance, the dipole reversal dance.
I'm available for weddings and bar mitzvahs as well.
Hello. I have a question to a friend. You talked about the 10% reconnection efficiency for Earth. Is that the same for Jupiter? And does the efficiency depend on the solar maximum or minimum, or is it on the size or compressibility of the magnetosphere?
Excellent question. Excellent question. Okay, let's talk about Earth for a minute. My understanding is that 10% is an empirical number. That is, if you look at the flows that are happening in the Earth's convection system and compare it with the upstream conditions, it's sort of 10%. And your question is superb. What does it depend on? Does it depend on the orientation of the upstream magnetic field? Does it depend on the strength of the magnetic field? Those are very, very good questions. And I wouldn't be surprised that there's a whole bunch of people who've been exploring this for the Earth. And I'm sorry, I just do not know what the numbers are and how they vary. But I am pretty certain that it will be a variable number, that efficiency. Now, when you go to different planets with different configurations, such as Jupiter, you mentioned Jupiter, we talked about how long it takes 5 hours to go from the day side for that flow to go over to the terminator, and then many up to 100 hours if you were to drive a Dungy cycle, and you're not going to have the solar wind, solar magnetic field being continuous. So the efficiency of coupling, I would imagine, is going to drop even if you had a Dungy cycle. But the other problem is that we talked about the viscous interaction on the boundary of Kelvin-Helmholtz interactions on the sides and so on. And the efficiency of coupling there is probably a lot lower. So, but it's a different process and will depend on different factors, okay? And so that rule of thumb of 10% is just a rough number to give you a gauge for the Earth. And if you then start applying it to other situations, I would love to know what that number is for Mercury. I'm sure Mercury scientists have estimated that number. Jim Slavin must have a number at the top of his head, but I'm afraid I don't. Yeah, good question.
And I'll just mention too that reconnection happens in induced magnetospheres as well, although that seems like maybe not something that would be obvious. Even in Venus with the draped magnetotail, we think reconnection happens there. Mars has the crustal fields everywhere that are spinning with the planet and oriented every which way. And so reconnection at Mars is happening just all the time. That's really fun.
But that's not Dungy cycle, that's
No.
small scale intermittent reconnection or
Correct.
boundary
Yeah.
reconnection. Yeah.
There could be
Okay.
something Dungy-ish within a crustal field for short periods of time where you get the circulation and then it rotates out of you and that stops. So,
Okay.
yeah,
Maybe.
Mars is great.
I think I saw that like probably just a few like months ago, but I think it's from several years ago. They were thinking about like putting at Mars's L1 like an artificial magnetosphere to like restore Mars like magnetosphere and atmosphere. What do you think about that? It seems like all wishful thinking, but
Yeah, is this being recorded? So,
It is, yes.
okay, got it. No, it's fine. Got it. So the at some point I was brought into that effort and then kind of withdrew from the effort. So whether or not you can create a global magnetic field for Mars today is beside the point as far as I'm concerned. If the purpose in doing that is to prevent atmospheric escape, A, we don't yet really know if magnetic fields protect atmospheres. And B, even if they do, the escape rates are low enough that it's not that big a deal. You know, the time scale for the escape of the Mars atmosphere is on the order of 1 billion years. So if you've somehow found a way to resupply the Mars atmosphere, then I wouldn't rush to protect it magnetically, even if that worked. I would instead start planning for a resupply of the atmosphere in 500 million years or something like that. Yeah.
I have a question for Fran. Can you talk about how BX and BY are incorporated into this overall Dungy cycle idea?
Yes, so there's always this emphasis on BZ, BZ, depending on which side of the Atlantic you are. And because it's that component that is the one that's primary for driving the Dungy cycle, the reconnection and so on, right, on the day side. But of course, if it realistically, I mean, it's usually 45 degrees, the field coming in to the Earth. That's average. That's the Parker spiral. But of course, it's varying, wiggling around back and forth and so on and so forth. And yes, I'm pretty certain there are pretty good statistics. That's one of the sort of goals of Themis and MMS and so on, these missions that explore the Earth's magnetosphere. I'm sure there's very good statistics on how the convection rate inside the magnetosphere varies with those parameters. I don't happen to know what those correlation coefficients are, but it's pretty certain that the BZ component is the crux, but the others have involvement, particularly depending on season because of the tip back and forth, and so on, and sideways. So there'll be a seasonal effect. But also there is what's called guide field reconnection, where you have a guide field, you have an opposite component, which is the BZ usually for the Earth, but you also have a guide field, and that will affect the extent of the reconnection on the day side and where it goes and so on. And you always have to think about how the field, you get a reconnection happening, but often you get a flux rope produced in that X region where you have the reconnection, and where do the ends of the field that go through that flux rope, where do they connect? And what happens to that field as it being carried downstream? So yes, it gets messy and complicated as always when you look closer. But you need to look at those other components as well. And it would be interesting to know as you asked, how does that coefficient of efficiency vary with these different parameters? And I'm sure there's a community of people who pulled that all together. I'm just not current with those current numbers. That would have been a good question for Bob Ergen. I wonder if he probably knows him. Yeah.
So I actually just had a comment. Fran, you were asking earlier about a frame of reference for the temperature of Venus. I couldn't help but do some Googling.
Okay,
So-
what do you find?
So Nick was right. A ceramics kiln is much hotter, like 18. So Venus is 800 or 900 Fahrenheit. Ceramics kiln 18 up to 2500. That's too hot. Same for like a bonfire or barbecuing coals. I looked at iron turns red hot at 1500 degrees. That's too hot. Aluminum melts at 1200. And so you're actually right. The cleaning cycle of an oven is about spot on, but it also turns out that's the optimal temperature for a wood-fired pizza oven. So you could make a great artisanal pizza on Venus.
That's interesting. But then thinking about bringing electronics to the surface, so at least your aluminum wouldn't melt. That's good news. But you would have to worry about your chips and electronics and so on. So we may have to have a cooling system. Or what I like the idea is a dirigible. You go into the atmosphere of Venus, you go down and you take pictures and you make measurements and maybe pick something off the surface. Then you go back up and cool off and drift around for a while and then you go back down again. So, you know.
But I also want to caution that those kinds of analogies only take you so far with Venus. You know, a pot of boiling water on your stove has lower temperature than the cleaning cycle in your oven. And I would, any day of the week, choose to put my hand in the middle of the oven
Ooh.
rather than a pot of boiling water because of the density. And
I-
at 100 bars or 92 bars on Venus, you know, add that in there, add that into your thinking as well.
Is
So it's
someone,
thermal energy versus temperature. Temperature is an average, thermal energy is
Yeah.
total energy.
I did a demonstration in class with the boiling water and I poured boiling water on my foot by mistake in class in front of
Totally different
300
demo.
people. Ugh. Had to get the TA to go get ice. Anyway, okay. Thank you, Peter. That's great. Good. Now we know.
I mean, as I said, I've partially forgotten the question, but the general idea was, you know, as you were talking, David, about atmospheric chemistry, loss, all of the various elements. So one thing also you didn't bring up, and I think you will, that's the thing I'm thinking ahead of it, you know, and trying to bring it up maybe. But the conditions that something like solar wind is playing, or solar energetic particles for not only loss, but for chemistry. And these are both from the sun, and couple that with cosmic rays. I mean, that's life-changing since you are also an astrobiologist. It's just very interesting, but they are connected to every planet we are on. And what are the various impacts? So that's one question, and we can go off to lunch, talk about and quantificate. One for maybe both of you, primarily for Fran. So are there any other planets in the solar system where we kind of see a pronounced bungee effect?
There's a significant what?
Uh,
Dungy cycle?
Bungee, not bungee. I keep saying bungee now. I don't know. This is what happens when I get tired anymore. Dungy cycle.
Yes. So Mercury, there is definitely a Dungy cycle. It's very rapid. It happens in seconds rather than minutes or hours. It's very, very rapid. And so then you say, well, there's no ionosphere, so you're not coupling the solar wind to the ionosphere. Actually, what you're doing is you're coupling the solar wind to the internal liquid region underneath, which are conducting. So there is, this was a discovery from the messenger that the conducting component comes from the interior. And so that's what the coupling is. It's between the solar wind and the interior.
Kind of similar to Earth then.
Very similar to Earth. It's just very small and very rapid. Remembering, of course, that the solar wind is so much stronger at Mercury's distance. So it's but it's definitely a Dungy cycle. It has all the configurations. It could be too that at, we believe at Ganymede also has a Dungy cycle. In this case, circular, the internal field of Ganymede, which is the same size as that as Mercury, there would be a Dungy cycle inside the magnetosphere of Ganymede. There's no trapped plasma. It looks like it's cycling through and removed. So that would be another place. It could be also that Uranus and Neptune, depending on their phases on their orbit around the sun, could also have Dungy cycles. No question. Yeah.
And I can jump into the first part and just comment about what my plan is for the afternoon, because I'm also happy to modify the plan in real time. But I was assigned Planetary Habitability I and wait for it, Planetary Habitability II as the 2 lectures. So in the first one, it was going to be mostly setting context, only a little bit of heliophysics there. What is habitability? What kind of worlds in our solar system do we think could be habitable? What do we know about exoplanets so far and the environments they're in? And then a little bit about the stellar and planetary influences on habitability writ large. The Planetary Habitability II is going to be all heliophysics with the primary focus on atmospheric escape and how heliophysics really contributes here. When I was putting things together, I was thinking back to my own experience starting to attend these interdisciplinary meetings with exoplanet people in the room and planetary atmosphere and climate people in the room. And I think for me anyway, kind of having the broad context was really useful. So that's some of what I was trying to give with part of my time today. Okay, so some of you just walked back in the room, so I'm going to do a soft start. And rather than launch into slides and material, just spend 1 or 2 minutes kind of taking stock. Every lecturer at the summer school has a different style, and now you have a sense of mine. And so the first question I have is sort of the level of interactivity and the types of questions I'm asking you to be interactive about. Does that feel okay? Do you want me to kind of breeze past those a little faster? Does it feel too juvenile? I tried to ask questions that I myself would be interested in discussing and that I think are not always so obvious. So you're okay with that? I'm not seeing head shaking no. And also I think that breaks it up a little bit more for both me and you. Okay, so I'll keep doing that. Pacing seem okay, or speed it up a little if I can. I don't want to slow down. Just do what you're doing as long as we end up where it says on the airplane ticket. Okay, good. Great. So here's Planetary Habitability I, a topic so important that there are two lectures for it. And the way I kind of broke this up is what can heliophysics take, or what should heliophysics be mindful of when engaging in thinking about planetary habitability? That's going to be this first part mostly. And then the second part is what can heliophysics bring to the table when it shows up at these meetings? What kinds of questions are pure heliophysics questions for people? So that'll be part 2. But there'll be heliophysics that kind of sneaks into this first one and non-heliophysics that sneaks into the second. So first, habitability as a general topic. And you may have been asked to think about this before, but I think it's still worth spending 2 or 3 minutes on. What is life? What are its essential characteristics? So within your tables, you have 3 minutes. Go. All right. I was close enough to 3 minutes. So it turns out whenever I say you have a certain amount of time, half the time I do that, I forget to look at my watch at the start. And so it's more just guesstimating. Instead of cold calling this time, just kind of offer answers if you can. We're all comfortable with me now. What is it, or what are its characteristics? What distinguishes it from non-life? Homeostasis, what is that?
Being able to like regulate your internal energy, like having some sort of autonomy over yourself, I guess.
Okay. Okay, regulating internal energy, having some autonomy. What else, if anything, here than there? What's? Yeah, chemical disequilibrium. Yeah. Yeah, that's one that's often thrown out. Yep. Reproduction. Good. What else? Say again. Sustainability. Okay. Yeah.
Sensitivity to some sort of stimulus, light, has to respond.
Okay. Anything else you came up with? Metabolism. Yeah, but that word comes up a lot when people talk about life. Adaptability. Yeah, adaptability to change. Okay, good enough. There's no universally agreed upon definition for life. Someone can look it up on ChatGPT and tell me in the next 30 seconds if they would like. But it's definite that any single answer that you just gave is inadequate. It's probably a combination of things. There are self-replicating software programs now, okay, that can adapt as well. All sorts of things. There are also some, in my mind, red herring examples. For example, all of us came from an egg originally. And so is the egg the life or are we the life? The egg is actually reproducing. And we are the intermediate stage back and forth. And so so I would have written all these down on the blue slide, but you get the idea. It's incredibly hard to difficult to define. There are some things that involve chemical disequilibrium, metabolism or respiration of some kind, interaction with your environment, the ability to evolve. All of these kind of get mixed into the definition of life. But the fact that there's no really clear-cut definition for life makes it harder to look for in other places because you're not entirely certain what you're looking for. And all we have are the examples that we've agreed upon here on Earth. So as of last night, when I updated this slide, there are around 8.7 million species of life on Earth. The last time I updated this slide was, I don't know, probably 4 years ago or something like that. At that time, I think there were 6.5 million species that people thought existed. This is the result of some statistical analysis and extrapolation. So around 9 million species of life on Earth. As far as we know, every single one of them requires 3 things. First of all, fundamental building blocks, so chinops or sponge, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. There's a big brouhaha in the community in around 2008 or so because someone thought they had found an additional building block for life, arsenic, by studying bacteria in Mono Lake in California, just west and a little bit south of Yosemite. That turned out not to pan out, but it got the whole community sort of worked up for a while. You can find those things in any planetary body, by the way, CHNOPS. That's not challenging. Source of energy also. All of us are sunlight driven in this room because we either eat plants that use sunlight to get their energy, or we eat animals that ate other animals that ate plants. So ultimately our energy is coming from sunlight, but there's bacteria underground and there are bacteria in the deep ocean where sunlight is not an energy source and they get their energy from chemical reactions or heat or something like that. So there should be energy sources on most planetary bodies that could be viable for life. How much energy is available to life is an open question. So Fran mentioned before single-celled life on Mars. From the papers that I've seen, that seems to be the most likely outcome because of the availability of energy on Mars should be less than the availability of energy on Earth to drive life. But then the most important one, and maybe the hardest to achieve on other planetary bodies, is water in liquid form. There could be other liquids that could be appropriate for life, but all life on Earth uses liquid water. And the key characteristics of water that we think are important for life are, number one, it's a really great solvent. And so it allows materials to mix together that are going to build amino acids and things like that that life uses. And it's a polar molecule, so that it's charged on one, positively charged on one side, negatively charged on the other. And so that allows the water molecules to kind of organize and orient themselves and things to be sort of passed through water in important ways. You can tell I don't really know a lot about how the polar nature helps. But there could be other liquids that help there. But hydrogen and oxygen are two of the most abundant species in the universe. So any other liquid, any other species, water is likely the most abundant species to exist as a liquid in the universe. It could be methane, CH4, but it uses carbon. So oxygen, I think, is more abundant than carbon in the universe. Number 3, and carbon is more like 6 or 8 or something like that. Yeah, so just on abundance of the chemical elements that make up the molecule. Yeah. What's that?
Could be carbon-based life.
Sure. Yes. I mean, we're a carbon-based life as well.
Some other being, as you said, water is not.
You're right. You're right. So here I'm distinguishing between the building blocks of life, and we're carbon-based life, and then the solvent, the liquid that allows all that stuff to mix together. And so in terms of the liquid, water is likely the most abundant liquid. But there could be others that work, and we'll talk about one in a minute. Actually, it's methane on Titan. Okay, phase diagram for water without all of the ice 9, ice 7, ice 8 stuff labeled there, just solid, liquid, and gas. And often on Earth, we think of water along the temperature axis, and water being liquid at appropriate temperature range. But if you're on another planet, you're not necessarily at 1 bar of atmospheric pressure. And so then the vertical axis of the phase diagram of water becomes important at that point. And so Earth here at 1 bar of atmosphere, the typical conditions for Earth straddle the solid liquid part of the phase diagram with conditions on Earth's surface that are favorable for liquid water over much of Earth. Okay, at Mars, we do have temperatures that overlap significantly with Earth temperatures in various conditions, but the pressure at Mars is 2 orders of magnitude lower, and you're down near the triple point of water. The range of temperatures at that pressure for which water can be liquid is very narrow. And so it's harder to have water stable as a liquid for long periods of time on Mars. And then Venus, let's not talk about Venus. Venus is it's way over here past kind of the critical point of water at the surface of the planet. Liquid water is not possible on Venus. However, you may have heard about life in the clouds of Venus. And the clouds of Venus, that cloud deck, exists at around 1 bar, so at lower pressure than the surface pressure, and at temperatures that do cross into the liquid part of the phase diagram of water, which is one reason that people think about life in the clouds of Venus. There are all sorts of other problems there, and I have a slide about that, but at least the pressure temperature part for Venus can work in the clouds if it can't work on the surface. Okay. Yeah. So for exoplanets, we can figure out temperature for some planets. Not only can we calculate an effective temperature from that energy balance, but for the exoplanets where we have measurements of atmospheres as a function of height, we can start to back out what the scale height of the atmosphere is. And the scale height is KT temperature over mg. So if you know the gravitational acceleration of the planet, if from the spectroscopic observations you have some idea of what the species are in the atmosphere, you can start to get a sense of what the temperature is from the scale height too. Pressure, I think there are, we don't really have pressure information about atmospheres. We can tell when it's optically thick. And so that can give you some constraints there. And I don't do this work. I do the atmospheric escape part. Okay. I don't know why that's like that. There we go. Habitable zone is a term that I'm pretty sure everybody has heard. It's an approximation term. It's, you know, it's not meant to be something super definite or super specific. It's supposed to give you an idea of where maybe to start looking on the surface of a planet that is orbiting a star. And so we can first start with our own solar system. Liquid water requires a surface temperature that's, you know, around 273 Kelvin. It doesn't have to exactly, you know, be exactly above 273, just in the ballpark would be fine. There is life in the, there's life in Antarctica where the average temperature is below 273 Kelvin, and there's still life there, but just get in the ballpark so that it can be above 273 for at least some of the time, and you can have liquid water. These are the two equations that I had up in the first lecture that relate the effective temperature of the planet to the temperature at the surface of the planet through the optical depth, how much there is in the atmosphere in terms of greenhouse gases. And then the effective temperature is related to the solar luminosity, how reflective the planet is, its albedo, and its distance from the star. So all those things play into where water can exist as a liquid on the surface of a planet. And this is all the concept of habitable zone tries to address, is for what range of orbital distances, for what values of little d, can you get a surface temperature that is around 273 Kelvin. And there's tons of wiggle room here. There's lots of latitude to make different decisions about what is required. So on the next slide, I can show you that different people do it differently. This is just a sampling. And I probably made this slide when I taught this class in 2021 or something like that. So there may even be new ones in the past 3 years. So you can compute the inner edge of the habitable zone as where the surface temperature is going to be too hot for water to be liquid or life to be viable. And that inner edge ranges from just outside the orbit of Venus today. Venus is at, you know, 0.7 AU or so, to beyond the orbit of Saturn here as well in one of these estimates. But most estimates put the outer edge of the habitable zone where you're starting to get too cold, either just inside the orbit of Mars. Mars is at like 1.54 AU, or just outside the orbit of Mars at 1.7. And in the exoplanet community anyway, I've started attending their meetings in the last 8 years or so. It seems like the Cooperative estimate is the one that most people in that community cite, perhaps because Ravi is kind of a card-carrying exoplanet scientist, but you know, so is Lisa Kaltenegger and Ramses Ramirez as well. But that gives you a rough sense, and also the sense that it's very fuzzy, the concept of habitable zone. It's sort of where to start thinking. Yeah. Yeah, so I don't know. It could be, you know, it could be that they started with an answer in mind and picked their values or tuned their calculations to make sure it came out right, or they picked values and it came out differently and that made them reconsider their values. I think that's very possible. But you know, also Venus, Earth, and Mars have considerable atmospheres compared to Mercury. So seeing something in at like 0.4 AU where Mercury is, I think that would be clearly alarming here. Whereas the other three, I think you could make arguments back and forth. Okay, that's habitability in general. Now let's go to specific solar system habitability, and let's start with Earth. This was supposed to animate so that you didn't read ahead, but go ahead and read ahead, that's fine. So let's talk about when, where, and how. First, when did life on Earth arise? We have no idea, but we have fossils that date back 3.5 billion years on Earth, and we have isotope signatures in rocks that are the kinds of isotope signatures that are unique to life, as far as we know. And those rocks are 3.85 billion years ago. And the concept of a late heavy bombardment for the inner solar system, as giant planets were shifting around in their orbits and jostled things in the Kuiper belt and threw a bunch of junk into the inner solar system. The date for that heavy bombardment period is around 3.8 billion years, between 3.8 and 3.9. That concept of a heavy bombardment has been called into question recently. There are some people who are thinking that maybe that didn't really happen, that certainly the giant planets shifted, but there was no increase in impactors. Nevertheless, it seems awfully coincidental that our earliest evidence for life is at the same time we thought that there was a really extreme impact environment. This suggests that life started really quickly on Earth as soon as it was calm enough for that to happen. And it may even indicate, you might even infer that life could have started several times on Earth and been snuffed out by impacts, snuffed out, snuffed out. It's only the most recent version of life that persisted to today. Okay, where we can do basically DNA proximity, DNA comparisons between different species on Earth. Turns out animals are eukarya, so are mushrooms, fungi, and we're really closely related to mushrooms DNA-wise. Much more closely related than mushrooms are to bacteria, which is, humbling, I guess. It keeps me grounded to think that. So these three branches of life, you can compare the DNA between all the different species, and you come up with this sort of family tree of more and more primitive DNA, and it suggests that there was some kind of common ancestor with a certain chemical representation in the DNA, and that common ancestor, the DNA of microbes near hydrothermal seafloor vents, seems to be in the ballpark of what we think the DNA of the common ancestor was like. It sort of makes sense that life may have emerged in our oceans. It's relatively protected there. I mean, it's a rough environment, but you're protected from radiation there. You may be more shielded from small impacts. And you can get your energy from the heat and chemical reactions that are happening there. That's where the microbes are getting their energy today. But it doesn't mean that life necessarily started there. So we find life pretty much everywhere we look on Earth. The Antarctic dry valleys, there's life where, it rains sort of once a century, and we find life there. We find life in really extreme environments as well, incredibly acidic, incredibly basic, really high radiation environments, all sorts of places where, we would be dead right away. But there are bacteria that can exist there. Fran.
Okay, so on Earth, we find life in very extreme environments. But everywhere on Earth is connected to a highly productive, living equatorial region. And we're connected by oceans, we're connected by atmospheres. So I don't think we can say, and you weren't actually saying this hinting at it, you can find extreme life on Earth, then why could life evolve and develop in extreme environments elsewhere? I say yes.
I wasn't saying that life should originate in extreme environments. I think that it originated in a relatively safe, I mean, if you call a hydrothermal seafloor vent a safe environment, I think that it could have originated there and then it adapted to extreme environments. I think it comes down to sort of likelihoods. And the more energy you have available to drive life, and the more sheltered it is from being snuffed out, the more likely it is to happen there. And I think some of these extreme environments are associated with low likelihoods. So more likely to evolve into those environments. But I'm not an astrobiologist in that sense. So take my opinion very carefully.
I know you put all these caveats around it, but people just don't include for that and so on. What it was, which I know it's not the surface, very careful to say, surface cover. But, astrobiologists, and particularly the exoplanets, just go charging off and go, habitable zone, habitable zone, habitable zone, when that's not.
Yeah, actually, I'm going to disagree with you. They don't go charging off saying habitable zone, habitable zone, habitable zone. They acknowledge that life might be more likely in oceans, in ocean worlds. There are these Hycean worlds, there are ocean worlds. And I think solar system astrobiologists think that those places are the most likely places for life to have developed. And we have a prayer of accessing that life in our own solar system, even though it's way harder than accessing potential life on Mars. The likelihood that it developed there versus Mars might make that a worthwhile trade. When you're starting to talk about exoplanetary systems, figuring out that there's life in ocean worlds there, what are you going to do? So they tend to restrict themselves to surface life when thinking about exoplanet systems because of accessibility, the ability to figure anything out in the first place. Okay, how? You may have heard of the Miller-Urey experiment. They put gunk in a jar, the kind of gunk that they thought existed on early Earth, and then they zapped it, and amino acids formed, and all sorts of organic molecules, which is pretty cool and suggests that this might be one way for life to have begun. But there are other interesting scenarios too. There are these ideas of warm ponds that might have been on the surface of the planet. And when you make a warm pond environment, you don't get amino acids out, but you do get structures that kind of resemble cell membranes that form naturally in those kinds of environments. And so it's not clear where life started on Earth or what conditions exactly were necessary, but we know zapping stuff can be helpful, injecting a lot of energy, and we know keeping stuff relatively calm can be helpful in different ways. In the warm pond scenarios, you actually do form RNA in some of those scenarios. That seems like a really big deal to me. And I have questions about why we don't favor that versus the seafloor vents, although the DNA of the stuff at the seafloor vents is most representative of what we think that ancestor is. So I don't know how much of a debate there is between these environments. What I'm carrying is that multiple environments might have worked. Yeah. Okay, Mars. So there's abundant evidence for stable past liquid surface water. We went through some of that in the previous lecture. There's an energy source at the surface, sunlight, and there's carbon and hydrogen and oxygen and all that stuff. Mars was habitable in the past, and evidence for past life might be present on Mars, and it might be more accessible than at other places in the solar system, like inside Europa's icy shell. Unless Europa can find a way to get that stuff out, then we have to find a way through that shell. So maybe more accessible, and it was habitable, at least in the past. Nevertheless, the Mars investigations that are astrobiology related are not looking for life on Mars. They're looking for habitable environments, past or present on Mars, not so much looking for the life. Is life active today is an open question on Mars. People wonder what the answer to this is. There's really controversial evidence for methane in the atmosphere of Mars, and I won't, Rebecca's representing kind of my opinion on the subject, but it needs to be represented. If it's true that there is methane in the atmosphere of Mars, that's a big deal because methane as a molecule has a really short photochemical lifetime, years or something like that, maybe 10 years or something like that on the outside. And so if there's methane in the atmosphere, then it should be broken down very readily. And so something is producing methane and putting it into the Mars atmosphere. One of the options for producing methane, as you know, is life. There are other geophysical processes that could put methane there. And the detection of methane at all in the Mars atmosphere is a point of contention. And this is one of those places where sort of extraordinary claims require extraordinary evidence, in my opinion. And I'm not sure that the evidence is extraordinary yet. Right, so yeah, to get into this, an orbiting spacecraft with an instrument designed to look for methane doesn't see any when it looks down at the planet. One of the landers, one of the rovers, says that it sniffs methane and that it varies seasonally. But it's unclear whether that data analysis was done appropriately with the right size error bars. It's also unclear whether it's sniffing itself, whether it brought methane along with it to Mars. Controversial evidence, yeah. There's also suggestions for subsurface hydrothermal systems on Mars. We see geomorphology and we see geochemistry that suggests that flowing warm water occurs beneath the surface. This would be a great place for bacteria on Mars. So there's some speculation they could exist today. Titan. So I'm down on Titan as an astrobiological target. But it's interesting. It's a great way to think outside the box. So let's at least give it that. So the requirements for life might be met at the surface. So there is no liquid water. It's too cold for liquid water at the surface, but there are lakes of methane and ethane, as Fran mentioned. And methane and ethane are liquids. So they could be solvents and they could be polar, but they're not polar. And it turns out methane's not a particularly good solvent. So if there is life there on Titan, it got a really raw deal in terms of the liquid that is helping it. There's really rich atmospheric chemistry. There's a whole nitrogen cycle. If you ever see a chemical diagram of Titan's atmosphere, you'll be scarred for life when you see that diagram. It is crazy. But organic compounds are produced in the atmosphere through the chemistry that occurs. There's a whole nitrogen branch. There's a whole methane branch, carbon branch, and it produces tholins and hazes and all sorts of gunk that's organic. The subsurface, as Fran mentioned, might be a better option. There is speculation that there's a liquid water ocean or a liquid water layer. I don't know which is a better word for Titan, but there's liquid water underground on Titan, so that might be okay. And the surface of Titan, future Titan, might be better as the sun increases in luminosity over time. I'm talking billions of years, future Titan. As it gets warmer, then the chemistry in the atmosphere is going to change. It might become more conducive with time. Icy moons. Here we go. So the requirements for life are definitely met. There's liquid water under icy shells. That liquid water is salty. You know, for Europa, we know this because there's an induced magnetic field from Europa coming from the ocean. There's a heat source in those oceans. These moons in the outer solar system are all tidally heated by the giant planets that they orbit. So they're flexing back and forth with every single orbit. So you can imagine, and other people have, James Cameron's cartoon artist has imagined, you know, hydrothermal vents inside Europa at the bottom of the ocean, and tidal heat is turning into energy that's heating the water around it, and that there may be, I don't know, squids swimming around or whales. I don't know if that's a fin or if it's just bacteria. And so what you would do is you would redirect Elon Musk to put his nuclear stuff on the surface of Europa and melt your way through the ice shell and then release a little vehicle that goes swimming around and visits the vents, or something like that. Yeah, moving on. Okay. Europa is in the most restrictive planetary protection class of objects. Europa and Mars, I think, are the two that we are most scared about contaminating or being contaminated by. And then, as I think Fran mentioned, there might be a way to get the material from the ocean out onto the surface. That might be this red stuff that we're seeing on the surface is kind of gunk and organics that was created in the oceans that finds its way up through cracks in the icy shell or diapirs in the shell as well. Some people think they're geysers on Europa. I happen to think that evidence is fairly flimsy. But regardless, I think it's quite possible, especially when you look at Europa, that the shell is like melting and refreezing, and stuff can find its way to the surface. And so that might be a way to explore whether, you know, life forms in Europa's ocean. It's a way cool object even without the life part of the equation. Yeah. That's one of the goals of the JUICE mission, but Fran probably has the range. How deep is the ocean? Yeah.
The goal of the Clipper mission is to find out how thick the ice is. And there are estimates that go from 1, which is super optimistic kilometers, to 20, which is the more pessimistic, maybe realistic number. And the main point about Clipper is to go and find out where the ice is thinnest. And it's carrying 2 things in particular that will help them with that. One is a radar, which won't get through 20 kilometers, but if there's anywhere where it's thin, they can find it. The other is a heat sensing instrument called THEMIS that will find out where there could be warmer water reaching towards the surface. And so there is a whole group of people who want to go and do a lander. They want to do that now, right? You know, they've watched the movie on Hollywood and they want to do it. And the answer is no, we need to do this systematically. We go there with the next spacecraft that flies by 40 times, images and tries to work out what the brown gunk is, tries to find out the best place to go, tries to find out what the next instruments need to be before you go there and sample it in any way. So this has to be done systematically and slowly, and you build up step by step. You know, the same could be said for Mars exploration, right?
Yeah.
You would probably agree, and a lot of the Mars people frustrated by that. So there's a little bit too much Hollywood in this, and we have to sort of step back.
Literally.
Yes.
You know. Okay, and Fran handed me these slides, and I think she kind of showed you, not this one, but maybe the next one. But this follows on from the icy moons idea. Yes, they're outside the classic habitable zone, yet they might be the most habitable places in our solar system. And just for fun, Europa, Triton, moon of Neptune, Enceladus with its tiger stripes orbiting Saturn, and maybe a hemispheric ocean or global ocean. These are the geysers from Enceladus. These are also the geysers from Enceladus. These are liquid methane or ethane. I always get confused which is going to be which for the lakes on Titan. Okay, methane. And we see the lakes kind of shrink and grow seasonally. And this is also Titan over here, looking down through the completely opaque atmosphere at an infrared wavelength that allows us to barely see the surface in that atmospheric window. Here? Sorry, here? This is false colored. This is infrared observations from Cassini, or radio. Or some long wavelength observation from Cassini that's false colored. And so they've colored the lakes black and blue, and they've colored the not lakes yellow. So it's just solid surface. Yeah.
Made of the same kind, like
I don't know if we know what the composition of the surface material is, but a cool aspect of the Huygens lander is that it was designed to land on either solid or liquid, because we weren't sure from looking at the opaque atmosphere whether it was going to be a global ocean or lots of lakes or no lakes at all. So they designed it to land in anything. Okay, and then Europa. I think we talked about all this. Europa is really cool. Okay, next. Venus, just a minute or two on Venus because I'm getting behind. But there was, during the peak of COVID, basically, there was a paper released in Nature Astronomy claiming a detection of phosphine gas in the cloud decks of Venus. And with that came the associated press releases and commentary that comes with it. And there's a lot of difference between the paper and the commentary that goes with the paper. And it's really a great kind of sociological study in science. And so I did this with my class when it came out. We spent 50 minutes on it one week. And later in the semester, when some of the rest of the community started weighing in, we revisited it again for 50 minutes and tried to look at the substance of the community critique of the science and separate that from the tone. And some of the tone was completely inappropriate, but the substance might have been pretty valid. Nevertheless, in the paper, the authors are extremely cautious, and they say that life is maybe the third best explanation for the existence of phosphine in the Venus atmosphere. They believe that they have detected phosphine in the Venus atmosphere, but some fraction of the community really challenges that detection because the phosphine line lies basically right on top of a sulfur dioxide line, which we know is abundant in the clouds of Venus already. But they found one place where there's a phosphine line not on top of SO2 and sort of took that and kind of ran with it. This debate is still ongoing, and I think it was rekindled a few months ago with some new telescope detections claiming, yes, we still see phosphine. But this all goes to the clouds as being a better possible place for life on Venus than the surface. I have major questions about how life could start in the clouds of Venus, unless it started on the surface, billions of years ago when it was more habitable and it somehow has persisted. Couch surfing on clouds for billions of years or something like that. I don't know. I think there are huge challenges there. Okay, exoplanets and habitability. So let's go to exoplanets now. Showed you, one version of a habitable zone for Earth. Here's another. So now we have the temperature of the star on the y-axis. And here's Venus, Earth, and Mars right here. Amount of sunlight received at the planet relative to Earth with 100% right here. And then this diagram has a conservative habitable zone. I don't know which paper they took this from. And they have an optimistic habitable zone that kind of extends into just outside the orbit of Venus. But their habitable zone goes outside of Mars in both cases. But stars exist in various spectral types. The mass of the cloud that condensed to form the star determines the mass of the star, which then determines how bright it is and how hot it is. That's why we have the spectral class. I went to undergrad in an astronomy program where one of the professors' names was Odell. And so we remembered the spectral classes by Odell's big ass final gonna kill me. OBA FGKM. That's how we remembered it. So we're a G star with a habitable zone. What did I do? They told me how to work it. Okay, there we go. We're at a G star, but you could go to a K star or an M star. Those are smaller, those are less luminous, those are, what happened? What happened here? Oh, it goes the other way. Okay, 25% of the sunlight is over here. So the habitable zone moves. No, wait, what? I think this diagram is wrong. Why? Yeah, why would, for a hot star, the habitable zone move closer to the star? It should move farther from the star. This is wrong. I put this up here to see how closely you were paying attention to the lecture. But hopefully you get the idea that the stellar type, the stellar temperature, influences where the habitable zone is. For M stars, the habitable zone, remember, very fuzzy concept, more of a general tool, the habitable zone should be much closer to the star. And for heliophysics, this has implications. Okay? The habitable zone is determined by luminosity, but M stars are more active than G stars, typically. So there are going to be more flares, more CMEs. The EUV from M stars is brighter, the flux at EUV wavelengths. And so an analogy would be Earth is sitting around a campfire, warming itself. An M star is a smaller, cooler campfire. So to keep the same amount of warmth, Earth would have to move in. But now you're close to that campfire and it's spitting sparks out all the time. And that's the heliophysics, the stellar activity, the flares, the CMEs, the stellar wind. So by remaining warm, you're putting yourself into a more intense environment heliophysically. And this can have implications for the atmosphere. Okay, how do we detect exoplanets? You've probably heard about all of these, so I'll go through quickly. But the biases are what I want you to pay attention to here. There's something like 5,400 confirmed exoplanets right now. The vast majority of them have been confirmed using the transit method. Basically a stellar eclipse. Whenever the planet passes in front of the star, the amount of light we see from the star dips. It dips very periodically. The amount of the dip tells us the size of the planet. So we can get size. The frequency of the dips gives us the orbital period, which, if we know anything about the mass of the star, also gives us the orbital distance. We can also do this hunt for planets blocking the star in different wavelengths. And an atmosphere will be optically thick at some wavelengths and optically thin at other wavelengths, depending upon what's in the atmosphere. Whether light from the star can pass through or not depends upon whether there's CO2 there absorbing light at very specific wavelengths. Okay, CO2 is a molecule, but so it's a band, but you get the idea. So we can learn about the atmosphere. The bias here is for large, close planets. The bigger the dip, the more likely we are to recognize that that dip is there. The more frequently the dip occurs, the more likely we are to catch it and see it repeating. And this only works if the planet is passing in front of the star from our perspective. So face-on systems, it's not going to work. Radial velocity is the method that was first used. And this is as the planet and the star do their dance around each other, conserving the center of mass the entire time. The star is wobbling back and forth towards you, the observer, which means the light from the star is getting blue shifted and red shifted, blue shifted and red shifted. We can take those shifts back out of velocity and back out the mass of the planet that had to cause that. We again get orbital period and distance. And if it's like blue for a long time and red for a short time, then we know that the planet's on an eccentric orbit. So we can get that out. Again, the bias is for large, close planets and systems that are edge on as viewed from Earth, so that the Doppler shift is towards and away from you. Yeah. So our sensitivity has been getting better and better and better over time. So the first planets that were detected were called hot Jupiters. So Jupiter-sized planets orbiting their star in a matter of hours. So really, really close to the star. But now we're detecting planets that are Earth size and Mars size, and there's one even that's getting down towards Mercury size. And it really depends upon the mass of the star and for the transit, how bright the star is. So I'll show you some data in a minute. Direct imaging, we only have a handful of these. This, of course, would be great. It's good for face-on systems as opposed to edge-on. And these are actual data showing you 3 planets orbiting a star. They're just repeated observations taken over a period of months. And you can see these 3 planets going around the star. You can get rough ideas about the mass and the size, but you have to understand, the amount of light that you're getting and how it relates to those things, orbital period distance, and you can do this spectrally and maybe get atmosphere information. The bias here is for large planets that are really bright, so maybe really young and still cooling, because we do this in the infrared, and planets that are far from the star, so we can successfully mask out the light from the star. There are other methods for detecting exoplanets as well, but the transit is the most common one, followed by radial velocity, and direct imaging is where people would like to be heading in the field. Okay, getting to your question, here's what we've detected so far. I encourage you to go to this website and explore. It's actually really fun. And you can make all sorts of plots. You can choose your x-axis, choose your y-axis, choose the bounds, color by some other thing. Here are the exoplanets that we know about. Semi-major axis is on the x-axis of the plot. How far is it from the star? Radius of the planet is on the y-axis. And for reference, here's Jupiter. This is where Jupiter would fall in this plot. And here's Earth right now. What's that? Oh, exoplanet. Whoops, I just typed it in manually. I didn't cut and paste. Okay, exoplanet.eu. Notice that there are things with Earth's radius, but not very many at Earth's distance from the star. We're finding a lot of planets around M dwarfs because M dwarfs are small and cool and not so bright. And big planets passing in front of them make a deeper dip in terms of the percentage of light being blocked. Okay, of the planets, there are some that are called potentially habitable. Again, this applies the very fuzzy notion of the habitable zone. And we have pictures of every single one that someone completely made up because we don't actually have pictures of the exoplanets. You can go to a list maintained at Arecibo, and this is the conservative sample of potentially habitable exoplanets. And it lists data about each one of the planets. On that same web page, there is an optimistic sample too. So if we become more liberal in our definition of habitable zone, we can add these 50 to the list. I'm just going to talk about 2 right now, briefly. Oh, no, I'm not. I'm going to show you this first. Here is lots of planets, not just the potentially habitable ones. Lots of planets, and stellar temperature is on the y-axis. This plot is correct. Stellar temperature is on the y-axis, and the flux coming from the star is on the x-axis. And the Jovian planets are the big ping pong balls. The Neptune planets are the little gray marbles, and then there are tiny little peppercorns sprinkled throughout there as well with sort of Earth-sized planets and super Earth planets. Another thing I should have mentioned is if you have a transit observation of a planet, you have its size. You know that the system is edge-on. So you can go do follow-up observations that are radial velocity and get the mass of the planet. And that's a really powerful combination. If you have size and mass, you also have density. So then you can sort of figure out if this is a rocky planet, if it's a Jovian type planet, or if it's something in between. And they're finding things in between as well. Okay, 2 systems. The super popular one is TRAPPIST-1, but it's becoming less popular because of heliophysics. And so about 40 light years away from Earth, it's a 7-planet system detected by transit. So lots of dips from planets passing in front of the star. It's around an M dwarf, and it's a really compact system. M dwarfs are low mass stars. They form from a low mass cloud, and so the whole system starts off more compact. The cool fact that I like is if you were on one of these planets and looked up in the night sky on your planet, you could see geologic features on the planet closest to you in the same way we can look up and see geologic features on the moon. Most of these planets should be tidally locked, just like the moon is tidally locked to Earth, so that the same side of the planet always faces the star. So you have a warm side of the planet that's always warm and a night side of the planet that's always night as well. The planets are also all in resonance with each other by gravitationally interacting. Their orbit periods are in small number ratios of each other, the same way that Io, Europa, and Ganymede are in orbital resonance with each other, a 4:2:1 orbital resonance. These are in resonance also. The orbital period of the planets is at max 20 days for TRAPPIST-1H, and the sizes are comparable to the size of Earth, 70% the size of Earth to 10% larger than Earth. What a great system to go looking at if you're interested in habitability or just Earth-like planets in general, terrestrial planets. But the recent papers, several of these planets, I think D, E, F, and G, maybe just E, F, and G, are all at the distance from the star that we think would put them in the habitable zone for this star. But recent papers about TRAPPIST-1, for example, I think Chuanfei Dong has one from Boston University, suggests that the stellar activity, the flares, the CMEs, the stellar wind are robust enough that none of these planets should retain atmospheres. So yes, they're in the habitable zone, but at least some current thinking suggests they're bare rock. There's no atmosphere there at all. Habitable zone is small. The other one, I don't know why I put it here, because I can't remember what planets you were assigned, but I thought this might be one. Is it? Yeah, okay. So Proxen B, closest star to us, Proxima Centauri in that system, 4 light years away. Well, we could like send little messages back and forth. That would be cool. And there's an Earth mass exoplanet orbiting that star. But it was discovered via the radial velocity or Doppler technique. It turns out the planet is enough out of plane from our point of view that it doesn't transit in front of the star. So we have mass information, but we don't really have size information about the planet, and we have no hope of measuring an atmosphere on that planet until we can directly image it. And directly imaging an Earth-sized planet, we are decades away from, very long time away. So this is a planet where we're not going to get too much more information out of it unless we become really clever. The effective temperature is, decent. It puts it kind of close to what you might identify as the habitable zone, and it's only a little bit bigger than Earth. There are also papers about this planet that suggest it should not retain an atmosphere because of atmospheric escape. We don't know if those papers are correct or not. Okay. I think I'm doing mostly okay on time. I go to 2:50. Nice. I think I'm on track-ish, within 5 minutes of on track. Okay, still on habitability. Biosignatures is what the exoplanet community that's interested in life and habitability talks about. And just like defining life, there's no single characteristic that we could take and say, aha, that is the thing that defines life. The same is true for biosignatures. You're probably playing a probability game, and detecting multiple biosignatures together would be way stronger than detecting any one thing. There's no single thing that's going to tell you. But with the transiting planets, we can get spectra back from their atmospheres. And I'll show you some on the next slide from the transits. As the planet passes in front of the star, the puffy atmosphere passes in front first. So the transit looks a little wider in that wavelength than it does at wavelengths that the atmosphere doesn't absorb. So you can get something called a transit depth as a function of wavelength. And that basically gives you a spectrum of the planet, as if you were observing it remotely. So we can play the same game for Earth, and we can look at a spectrum of Earth from outside, and this is an idealized one. But there are all sorts of things in Earth's spectrum, from near infrared, all the way into the optical and into the near UV, they're parts of that spectrum that we think are influenced by life on Earth. So for example, you can have absorption features from methane. That doesn't mean that there's life there, but we know that life on Earth, emits methane. So it's at least something to get a little bit excited about. If you see carbon dioxide absorption, then there might be volcanic activity on that planet. Water, at least that species existing in the atmosphere, means that there's potential for there to be liquid water someplace there as well. There's a kind of controversial thing called the red edge that you would see in Earth's atmosphere, where photosynthetic life, you see basically as you're moving into the red from the green, you see a jump in the spectrum at the red edge, and that indicates the presence of plants. Who knows if plants are developing on exoplanets? But any life on exoplanets at the surface is getting its energy from someplace. So maybe there's some spectral signature of absorbing the star's light. And then here, blue sky, the color of the sky in the optical and indicate a little bit about what the atmosphere is made of and how dusty the atmosphere is, and also tell you amount. Also frequently discussed are ozone signatures. Ozone in Earth's atmosphere, O3, did not exist, we think, in abundance until the great oxygenation event in Earth's atmosphere around 2.5 billion years ago or so, when oxygen started to be pumped in the atmosphere and actually last there. So when bacteria started pumping oxygen out, it didn't last in the atmosphere. It reacted with the surface right away. As sort of the surface receptors became more and more used up, then the oxygen started to linger in the atmosphere longer and longer. That O2 in the atmosphere photochemically reacts with sunlight and rearranges and becomes O3, which then the ozone layer ends up being contributing to protection from radiation on Earth. So it's an example of life helping itself in terms of protecting itself on Earth. So finding ozone in an atmosphere could also be suggestive as well. Again, none of these are ironclad indicators that life exists. And there's some pretty complicated chemicals that people are now thinking of as biosignatures, like methyl sulfide and things like that, that have lots of species listed in the compound. Yeah. Yeah.
So curious, like obviously life anywhere, always survive. Do that. But there's probably like an easy back of the envelope calculation. Is there some already packaged argument for why it's not worthwhile looking at that? And what the first thing I'm thinking of is the power is going to fall off like where, so it's not feasible for a thing to transmit like that. Power.
People definitely look for that. And so, Jill Tarter from Cosmos? No, Contact? Anyway, yeah, I think Contact. Jill Tarter, listening with radio dishes, that's SETI. And so there are people listening for radio signatures. So broadly, these are called technosignatures, and technosignatures can fall into active technosignatures and more passive ones. And so listening in the radio is something that people have been thinking about since the 50s and doing since the 50s. And so, SETI out in the Bay Area of California basically sort of built up in this way. There are meetings and there are even online seminars that happen every couple weeks for the technosignature community. There are people in the US who think about these. And what are some of the other signatures of more advanced life? Like, could you see our cities if you were in another system? What are the signatures of our population centers? And so those would be more passive things that we're not actually trying to broadcast, but are still detectable. So there are people who think about it. I think 10 years ago, a lot of people thought that that was a pretty fringe community, but it seems to be gaining more and more acceptance, and that's my opinion.
I guess another way of phrasing my
why not put all our resources into that? Seems like the most straightforward, it's all kind of roundabout way.
Yeah, your comment on that? Go ahead. Yeah, there's that. Oh, go ahead, Farzad, and then I'll go. Yeah. And yeah, I agree with this. And, you know, some of this same issue crops up in looking for these signatures, and we don't always know what we're looking for. In looking for life elsewhere, we've assumed that life on Earth is what all life will be like. So those assumptions are built in. Another assumption, however, another thing that I think makes it maybe problematic to put all your eggs in the technosignature basket is that an intelligent civilization is a result of an evolutionary pathway that may or may not happen even if life itself forms. You know, there's a certain amount of energy required, a certain amount of stability required. There are lifetimes associated with intelligent civilizations that may be very short compared to the life of a planet. And so you might be looking for a very low probability signature that could be more unambiguous than some of these, but is much less common. Yeah. Okay, let's see how much I have left. I know I have 7 minutes, I think, still. I go to 250, right? 1. Okay, that's a very sharp distinction between the two. It's not sharp at all. So James Webb has revolutionized this, looking at exoplanet atmospheres. The data are amazing. The exoplanet atmosphere data that we had prior to this, that the community had, probably would have been 2 or 3 points in this wavelength range, each of which had vertical error bars like this and horizontal error bars like this. So it was really hard to constrain anything previously, and Webb, as you know, people are agog at the data coming back from Webb. So here's a hot Jupiter exoplanet, WASP-39b, which is the one they first looked at because they already had some indication that there was stuff there to look at. And you can see the richness of this signature with absorption from water, carbon monoxide, sulfur dioxide, sodium. You can start to really get a sense of what stuff is in the atmosphere. And also there are kind of maybe less exciting spectra to look at, but still scientifically super interesting. So this is 55 Cancri E. E means it's B, C, D, E. It's the 4th planet around that star. And the data are these points here with kind of big error bars, and these yellow points as well from 2 different instruments on Webb. And even with the big error bars, you can distinguish between the planet having a rock vapor atmosphere and the planet having a volatile rich atmosphere. And so this is an atmosphere, even though we don't have a lot of information about what exactly is in it, other than you know, some carbon and oxygen bearing compound, we can still kind of rule out models for what it's like. Okay, 5 minutes. Planetary influence on habitability. I just want to ask you, what properties of a planet do you think, and this will be the last thing, that there's only like 2 more slides after this, and I'll just move them into habitability too. So what do you think are the properties of a planet that influence its habitability. Yeah. Temperature, surface temperature. Great. Geologic activity. Okay. Yeah, good. So geologic activity. Say again. Surface pressure. So if it has an atmosphere, how thick is that atmosphere? Okay, so orbital characteristics and whether it's in synchronous rotation. Yeah, I heard something here too. Chemical composition of the bulk planet itself. Yep, totally. Yeah.
Radiation environment.
Radiation environment. I think of that as more a property of the star, but what about the planet could influence the radiation environment? Potentially. Magnetic field, potentially. Okay, you're right. There's the radiation from below. Yeah. Turns out uranium planet's not so habitable. You're right. It's like a zillion things. You know, you've only scratched the surface. So the chemical composition is, gonna determine to some extent how much heat is in the interior in terms of radioactive elements incorporated. It's also going to determine how the core freezes out and whether a dynamo is possible and how long-lived it is. It's going to determine what kind of surface materials they are and whether you're in an oxidizing or reducing environment. The outgassing from the inside of the planet is going to determine the atmosphere and its composition, the tilt of the planet, the spin of the planet, whether the planet has a magnetic field, whether it has moons. There's so many things that influence habitability. And this is definitely something for heliophysicists to keep in mind, that it can be okay for heliophysicists to say not habitable because the atmosphere should have been stripped away. It's not okay for heliophysicists to say habitable. It has a magnetic field and should have retained an atmosphere, because there's so many other planetary characteristics that could just screw everything up. And so this is what's fun about going to some of these meetings, is everybody is bringing a piece of the puzzle and you're all learning from each other, which is totally fun. So I'm gonna skip these other slides and come back to it, but there's one slide at the end I want to show you in the context of these meetings. Don't worry, that was actually quick to go through. So this is where I was on Saturday and Sunday. I was at the Goldschmidt conference. I've never gone there. In Chicago. It's a conference on geochemistry. I'm like the farthest thing from a geochemist that you have ever met. Like, you show me a triangle diagram and I will show you a sleeping Dave immediately. I had no idea how to interpret those things, but there was a workshop in advance on exoplanet composition, mineralogy, and evolution. And in that context, I was the exoplanetary magnetic fields person, but talking to people who do mantles, melts, and crust, talking to people who do chemistry in disks, talking to people who think about white dwarf planetary systems. So these planetary systems should be completely pristine. You shouldn't see any heavy elements in the atmospheres of white dwarfs at all, but people are detecting polluted white dwarfs where we can see silicon in the spectra of these atmospheres. And the inference is that planets that were orbiting that white dwarf, or asteroids, or dust, has fallen in to the star, and we're detecting broken up stellar system stuff in atmospheres of white dwarfs. So this is what can be really fun as a heliophysicist, to go to these meetings and kind of learn really broadly about something and bring your own contribution that everyone there values. I'm finding it really fun, and for me, kind of a new phase of my career where I'm climbing learning curves all over again, which is really great. So I think I'm 1 minute over. Let me stop there.
One of my beefs about exoplanets is why the heck can't they give them decent names? I mean, 438b, who gives a toss? Tom, Dick, Harry, anything.
Yeah. So there are people who are giving informal names to exoplanets, and it is totally not catching on, and I don't understand it. You know, Gliese 667 CC, that's what people say when they're walking around in the hallway. And I cannot tell one Gliese apart from another when, you know, Zach Berta-Thompson is talking, but everyone else seems to like nod and smile. Okay, two things. One, a discussion with Nippreet helped me a lot. For those of you who go on to teach in your career, you will have these moments too, where in front of an entire class of people, you realize you do not actually understand the thing that you are showing them right then. So that happened to me. I think this diagram does make sense now. And the x-axis is reversed. So the x-axis is the amount of starlight on the planet relative to sunlight on Earth. M-dwarf stars should be at the bottom of the plot. They're fainter than the sun. And so the habitable zone should move closer to the star. And I think that's what this plot shows, rather confusingly. But I think the habitable zone is moving towards the lower starlight side of things for the small planets. This is not how I would choose to show it, and you can, but this was the image of stellar habitable zones on the Wikipedia page for habitable exoplanets of all things. So I blindly trusted it. You can find much better plots. I cannot, no. I still, if I had to go back, I would not use this plot again, and I will not use this plot again. And I've never used this plot when teaching before, actually. I've used a different one. And for this presentation, I dropped it in. I was like, oh, I guess the standard plot has changed. And it turns out I don't like the standard plot. But if you, Nippreet Googled it, and we can find ones that we like better, and we can find ones that are equally confusing to this one. Okay, next. I want to go through a couple slides here that are heliophysics related. I'll do them quickly, but they were kind of related to what Lika brought up, and I'm going to focus on just this for a minute and then do questions. Is that okay? So stellar influences on habitability. This is where we're really getting into heliophysics at this point. I don't know why that's like that. Okay. There are stellar energy sources for planets that can influence the atmosphere, can influence habitability in different ways. And broadly speaking, you can classify these as photons, particles, and fields. So photons, within photons, the total luminosity of the planet is important. That's, you know, what we've been talking about a fair amount. It warms the planet's surface, helps determine the surface temperature. And here is a spectrum of the sun in black, and then Barnard's star, which you might have heard of Barnard's star. It's an M-dwarf, a relatively nearby M-dwarf star as well. 4,000 angstroms is here at the right. You know, 6,000 angstroms would be over here. So this would be red as you move into green and blue. And then over here at 2,000 angstroms, you're in the UV. 2,000 to 3,000, you're in the UV. UV can drive chemistry in planetary atmospheres, and so the spectrum of the star can be important in that way. Ozone absorbs UV light. There's UV radiation on the surface. That's why we wear sunscreen, hopefully. And then it can damage DNA, UV. And then finally, EUV X-ray emitted from stellar coronae. A decreases over time from a star, as opposed to the luminosity of a star, which increases over time. And that causes upper atmosphere heating, upper atmosphere ionization, and then indirectly causes escape. So all these different photon inputs are important. Particles as well. There's the stellar wind that can drive escape, can drive, it can create an induced magnetosphere, drive currents. It can also deposit particles. I don't know if we'll get too much time to talk about this, but it turns out the hydrogen and helium content of some planetary atmospheres might be greater today because solar wind particles are being captured by the atmosphere. And this is something that people don't think a lot about. And I have a student that's been working on this, and it could be quite important. Stellar energetic particles as well, more energetic than the regular stellar wind, can cause heating and escape, can drive chemistry in the atmosphere. I'll show you a plot of that, and also contribute to the radiation environment. Finally, fields by themselves are not an energy source, but when you couple a field with a flow, then that can create an electric field which accelerates particles. And so the field that the stellar wind carries, the interplanetary magnetic field, when accompanied with a plasma velocity, can be an energy source for planets and their atmospheres. Again, I don't know why these are animated. This shows that earlier in time, the EUV flux from our star should have been greater than it is today at many different wavelengths at extreme ultraviolet and X-ray, in extreme ultraviolet and X-ray. There's a better plot than this. There are actually a lot of data points represented in the shaded region. It's not a 2 data point plot, but there are observations of other G-type stars. And this is a really very tenuous, makes everybody super uneasy analysis, way of getting at the strength of the solar wind as a function of time in a star. I can talk more about how this is done and why it unnerves everyone, including Brian Wood, who developed the technique. But we know of no better way of getting stellar wind from other stars right now. And then even older, going back to 1980, theoretical analytic calculations that the magnetic field from a star should decrease over time. The strength of the IMF should decrease over time. One more slide here, particle inputs for Earth. You could generalize this to other atmospheres as well, but this shows the ionization rate in Earth's atmosphere as a function of altitude, and the shaded bands show you the different energetic particles that are depositing themselves in the atmosphere and creating ionization at different altitudes. So at the surface of the planet, it's galactic cosmic rays, charged particles coming from outside the solar system. And as you move up, solar proton events become, where did I go? Solar proton events become important. As you move up higher, even higher, relativistic electrons, auroral electrons, and then solar EUV and X-rays. So solar energetic particles are depositing their energy a little deeper in the atmosphere, maybe near where auroral electrons and relativistic electrons are. So different particles have different consequences for different parts of an atmosphere, and understanding the full particle spectrum can be really important. One example are some lab experiments where Kobayashi et al. A couple decades ago put carbon monoxide, atomic nitrogen, and water in a chamber. And then they shot 3 MeV protons into that chamber, and they got amino acids out. They got glycine, alanine, and aspartic acid. So putting solar energetic particles or stellar energetic particles into an atmosphere can create the kinds of chemical species that can be important for life, or could create false biosignatures as well, this energetic particle input. And one more example is, and we can talk about this work sometime, but I think the idea is intriguing and the details need to be looked at by many groups. This is the idea that atmospheric chemistry can be influenced by stellar energetic particles. So they built a chemical model of Earth's early atmosphere, and at a time when life had not yet arisen on Earth. And so nitrogen wasn't being fixed in the atmosphere by life. And they showed that if you put not only photons, but energetic electrons and protons into that chemical scheme, you can create a chemical pathway that does fix nitrogen on early Earth. And this happens at a time when the magnetosphere is more receptive to particles from the outside, where the polar cap of the magnetic field is really large, much larger than it is today, if I remember correctly. Rebecca. Great, thank you. So I've pulled it from a review paper that attributed it to Arapetian. So probably, okay, it came from Dan originally. Nice. Okay, that's all I had that I skipped last time. So now I can take questions if you'd like, and then we can decide collectively what we do next here. I'm not going to do that. I can just keep talking. That's fine too. Yeah.
Well, I have one then. I was just curious, sort of at the end, the final conversation about what characteristics of a planet could affect habitability. Do you think there's any way that gravity, the gravitational acceleration of the surface, can play a role in making somewhere more or less habitable, or is that not really an important factor?
Sure. Indirectly, for example, and I think gravity is really determined by size of the planet, size and mass. So I think that determines how likely escape is and how easy escape is and which escape processes are viable and which are not. So that's one indirect way in which it matters. I'm having trouble thinking of others.
Pressure.
As well. Yeah, true, how compact the atmosphere is, what the scale height is, which will influence densities at the lowest elevations. I don't know, I think yes, but my way of skirting the question is that gravity is determined by size, and size definitely influences. Because size is also going to influence the amount of internal heat that the planet has to drive geologic activity, to drive outgassing, to potentially drive plate tectonics, to create a magnetic field. So all of this is wrapped up in size.
Yeah, okay. Have people looked at rogue planets at all in terms of habitability, or they just kind of give up and say there's too little probability for that?
I wonder where that question is coming from. I do not know in terms of habitability, and rogue planets is something I haven't really engaged with very much so far. I take that back a little bit. I have heard one talk on rogue planet atmospheres that had one sort of habitability sort of slide to it. So there it's at least one person thinking about it. But I think most people and I guess now in this room, they're like 9 or something like that. But I think in the exoplanet biosignatures community, most people are trying to think about M-dwarf planets versus, G-star planets, which spectral type is best and things like that. I think most of the emphasis is there right now and on picking the appropriate list of biosignatures.
This is probably not very related to habitability, but I was just curious if there have been any observations with JWST regarding moons on these exoplanets.
I can address your question, but not answer it. I don't know if there have been dedicated JWST observations. There have certainly been JWST transit observations, both primary eclipse and secondary eclipse. And the primary way to detect moons, as far as I am aware, is through transit timing variations, TTVs. So the transit happens just a little bit earlier or a little bit later than you might have predicted. And it's because the planet and the moon are orbiting their common center of mass. So the planet kind of enters the frame a little early or a little late. And so far, there have been no positive detections of exomoons with any observatory that I'm aware of.
on that note, like how much work or how much thought has been put into habitability in smaller objects like asteroids and
Oh, interesting question. I'm not really aware of any focused efforts thinking about small objects or asteroids. Mostly what I hear about there is sort of the panspermia idea, and that's not asteroids so much as it is, you know, bolides or meteorites splashed off of a bigger planet, carrying life, and then, you know, landing on Earth or landing on Mars or something like that. There might be people, places thinking about that, but I'm not aware of it. And I haven't heard anything like this at meetings that I've been to. But it's an intriguing idea. So maybe the Expanse, the show The Expanse is sort of leading the field in this area. I don't know. Yeah.
Any others? Once. On
Go.
Planetary Habitability II.
Two. Okay. So I've told people before that I could talk about science all day, and I never really expected anybody to call me on it. So here we are. So let's go. And I'm going to talk about atmospheric escape, and then after discussion with Nick too, I want to make sure that I leave maybe 10 or 15 minutes at the end to also talk a bit about my own research. I was going to cut out my own research in the interest of giving you kind of the more general topics, but Nick encouraged me to talk at least a little bit about stuff I work on directly. So at 4:15, maybe, Nick, you can tell me, and then we'll jump. Okay. All right, here we go. Yeah, that cover image, this is just a quick interlude that everybody contributes to successful science communication. That cover image right here was made for the MAVEN spacecraft mission when we were doing some of our first result releases. So we interacted with the NASA Goddard Visualization Studio to create an image. And so the PI asked me if I would interact with them for an image. And so I sketched the thing on the left in 2015, and I sent it to the people at NASA Goddard, and they turned it into the thing on the right, which is now like on coffee mugs. It was on the cover of our senior review proposal to get extended mission funding. I cannot believe how they turned my crappy Pictionary drawing into that. And so sometimes when I'm talking to students who aren't all majoring in astronomy or physics, I kind of make the point that there's an opportunity really for everybody to contribute. And when you think about spacecraft missions and all the different skill sets there, not just the engineers, but even the administrators and the budget people and the artists, everybody kind of contributes. So that's just a quick point. Yes. So right, and so the data really come in my sketch. These are, no, I'm just kidding. So they took a test particle model from Xiaohua Fang in our community in response to my sketch. They had him contribute particle trajectories, and they're colored by the energies of the particles that he predicts as they're escaping from the planet. So there is real science in there as well. Okay, general requirements for atmospheric escape. On a scale of 1 to 10, with 10 being most tired, how tired are you right now? Didn't even respond, so I'm going to assume that's 13. Okay. That's fine. You're going to have to answer anyway. So what are the requirements for, okay, wake yourselves up. You have 90 seconds in your tables. Ready, go. What are the requirements to escape from a planet's atmosphere? And I'm going to use that time to get more water. I didn't look at the start time again. I don't know. 20 seconds left. All right. Discussion has died down. Someone give me one. Velocity. Okay, some energy source or ionization source goes up. Okay. Magnetic field, potentially. Gravitational potential, potentially. Okay, here we go. I'm gonna tongue-in-cheek say that they're three. Energy, it goes up and it doesn't crash into stuff on its way. The particles in this room have a very low probability of escaping anytime soon. The diffusion timescale for hydrogen in the Mars atmosphere is decades. Okay, so it's not happening from the bottom of an atmosphere unless there's a big asteroid impact or something like that, in which case this doesn't matter anymore. Okay, so you need escape energy, balance between the kinetic energy of the particle and the gravitational energy required to escape gives you the escape velocity. So 1/2 mv squared is the escape energy. So the escape velocity for Venus, Earth, and Mars is shown in the table. Gravity is important. And the energy that is required for each of those particles to escape is also given in the table. For people who build charged particle instruments in the heliophysics realm, they're often building electrostatic analyzers that are tuned to measure the energy of the particle as it leaves. So 0.1 EV, that's a really difficult charged particle measurement. With MAVEN, we think we can do that. 2 EV can even be pretty challenging for a charged particle measurement. 10 EV is usually okay. And you know, these electrostatic analyzers often go up to like 20 or 30 kilovolts or something like that. So escape energy from Venus, Earth, and Mars is actually relatively low when you're thinking about making measurements. You have to make sure you make your instrument really well. It has to be going upward. This will become important when we talk about photochemical escape, which involves dissociating a molecule and giving each one of the atoms energy. The energy that's given to each atom is sufficient to escape Mars. But because it was a molecule with a bond, only one of them is going to escape because the other one's going to go the other direction. You can't have both of them escape. And then collisions I just talked about. Scale height is on the left, kT over mg. The mean free path of a particle between collisions is on the right, 1 over the local density times the cross-section for collision. As density goes up, your mean free path gets smaller. You can travel less distance between collisions. As the cross-section gets bigger, your mean free path gets smaller. You can travel less distance between collisions. And the classical definition of an exobase is the location in an atmosphere, the altitude in an atmosphere for which the mean free path is approximately equal to the scale height. It doesn't mean that suddenly you stop colliding above the exobase and you immediately start colliding below. It's a gradual transition that happens, but we just tend to draw the line there. Okay, those are the 3 requirements. And then other things that you said may influence escape. Finally, the escape is happening from the top of the atmosphere. So there are reservoirs for escape. You're going to hear all about the ionosphere tomorrow. And hopefully that the ionosphere is formed from the thermosphere as well. And then above the exobase region, you know, the thermosphere continues upward, and we think of the exosphere as being collisionless. Collisions can still happen there. They just become much more rare as a function of altitude. So I give you a rough sense of the heights for Venus, Earth, and Mars of these three regions and the kinds of species that you see there. You're going to hear a lot more about this tomorrow, and I'm tired, so let's move on. Okay. Atmospheric escape processes. I find in the exoplanet community, especially when I go talk there, and people haven't heard me talk before, that atmospheric escape is a single process for people coming from that background. And we know in heliophysics that it's an array of processes. There are lots of different processes that can lead to escape, but they're driven primarily by interactions with the host star. So there are extreme ultraviolet and X-ray wavelengths. I'm gonna lump extreme ultraviolet and X-ray all together and just call it EUV for the rest of the time because I'm lazy. So EUV means extreme ultraviolet and X-ray. And then there are the particles coming from the star. Solar wind, stellar wind, and solar energetic particles as well. And these can interact with, let's say, a Mars-like planet in this case, because the Goddard visualization people made this for me for Mars, that has, you know, an ionosphere formed by interaction with sunlight. So it has charged particles there. Okay, so they give me a whole bunch of other slides showing the processes, but I'm not going to show those there. I'll just show kind of the end result. And this isn't it. So depending upon who you ask, there are as many as 10 distinct escape processes that could occur at a planet. So this is from a colleague of mine, Guillaume Gronoff, who wrote a really large review paper on atmospheric escape and has this really nice diagram with 10 slices of pie, each one representing a different escape process. So there could be as many as 10 different sets of physics that we talk about when we talk about escape. I tend to be a little more reductive. So there could be as few as 4. And I actually carry 4.5 when I'm describing escape. So let's just call that 5 since we're friends. And so the 4 processes are illustrated here, and I think they're self-evident. So I'm just going to move on. I'm just kidding. They're not self-evident in any way. So the blue is hydrogen that's escaping thermally. Genes escape from an atmosphere, and we'll talk about that in a slide. The violet oxygens are escaping photochemically through chemical reactions driven by sunlight. Some of these, someplace, oh, maybe none here, should be crashing back. Oh, sorry. The yellow and orange is ion escape, charged particles escaping in the stellar wind, in the solar wind. Some of those ions are crashing back into the atmosphere and splashing stuff out. That is sputtering. So those would be the 4 main processes. The thermal escape of hydrogen, though, I'm going to divide into 2 separate categories, and I think of those distinctly. One reason I do that is because exoplanet scientists think about one version of thermal escape when they are evaluating escape from exoplanets. 80% of the literature you will see on escape from exoplanets is just thinking about hydrodynamic escape, not thinking about any of these other processes. So this is one thing heliophysicists can bring to the table. In what? They are on ballistic trajectories, I guess, but still escape. I don't know. Okay, off we go. Thermal processes, everything's a Maxwellian. So that's really the explanation. So you have an ensemble of particles interacting primarily through collisions, which is happening near the exobase and below. You can describe that ensemble of particles according to the average energy. And so that's what we take as the temperature. You can associate a velocity with that temperature that we call the thermal velocity. And you can compare the thermal velocity to the escape velocity of the planet. So you can think of these as probability distributions. This is a hot gas in red, a cold gas in yellow. And it turns out the hot gas has a fair amount of particles, a fraction of particles that are above the escape velocity of the planet. So those particles near the exobase are going to escape away to space. This is Jean's escape or thermal escape. Okay, we evaluate how important thermal escape is a couple of different ways. The main way that people do this is by computing what's called the escape parameter. And it's counterintuitive to me. It's upside down from what I think it should be. I think we should rename it the retention parameter, the way it's set up, because it turns out low values of the escape parameter means thermal escape is more likely to happen. And you can see that because it's a ratio of escape energy to thermal energy. So when the thermal energy of the gas is large compared to the escape energy, then escape is more likely to happen. Okay, given that, you can compute a flux of escaping particles, thermal escaping particles, and this is sort of the canonical formula, and you can look at the variables in that formula and convince yourself that this at least qualitatively makes sense. I won't walk through that now for time. And there are updates to this, there are corrections to this formula that you can make because the Maxwellian itself is kind of reconfiguring itself as escape is happening. So you have to modify this as you're going along if you want to be really careful. If you're giving it to, juniors and seniors for a homework problem, you say, just use this. This is fine. Okay, when the escape parameter gets to be below about 3, then thermal escape becomes really vigorous. A significant fraction of this Maxwellian distribution is above the escape energy at that point. And so you get a fluidized outflow from the planetary atmosphere. It's no longer really useful to think about individual particles escaping thermally. They're all colliding with each other and bumping into each other as they try and get out of there because they're so hot. And when that happens, you get a fluidized wind, or sometimes it's called blow off, sometimes it's called outflow. Turns out astronomers call it photoevaporation, which I don't like that term at all. But as long as we all know what we're talking about, it's okay. And this is really interesting too, because you can meet the hydrodynamic escape condition for hydrogen, and hydrogen can be flowing out of the atmosphere as a fluid, and it can be bumping into heavier stuff and dragging that along as well. So exoplanet astronomers tend to evaluate the blow-off condition for the planets that they're studying. And if it indicates that hydrodynamic escape is occurring, then they say hydrodynamic escape is occurring, and they either apply a little model or plug in a formula, and they're done. And this is understandable that they do this. First of all, if hydrodynamic escape is happening, no other escape process is important. This is the beginning and end of the story if that's happening. Also, it's based on things they have a prayer of measuring, unlike some of the other processes. So they tend to cling to hydrodynamic escape. But where it gets interesting is when they find that hydrodynamic escape is not happening. That doesn't mean escape isn't happening. Escape can still be vigorous for some of the other processes. It can even be fairly vigorous for thermal escape. It just means hydrodynamic escape isn't happening. And so they tend to stop after evaluating hydrodynamic escape. Okay, non-thermal processes. Let's just march through those quickly. I've already described them qualitatively, so this will go fairly fast. Photochemical escape, you can have exothermic chemical reactions that are driven by sunlight. So the classic reaction is for the upper atmosphere of Mars. And you have molecular oxygen at the top of the atmosphere that originally came from the 95% CO2 in the atmosphere. The top of the atmosphere, that stuff starts to break apart. You have molecular oxygen. You ionize it with UV sunlight. And so now you have a molecular oxygen molecule, molecular oxygen ion wandering around. If it bumps into an electron, it recombines, but that reaction is exothermic. And what recombines, it splits apart the molecule, and you get two hot oxygen atoms or fast oxygen atoms moving opposite directions, each of which has enough energy to escape Mars. Turns out Venus is enough bigger than Mars, has enough extra gravity that this doesn't work on Venus. You still produce the hot oxygen, and they still go up into the exosphere on bound trajectories, but they always fall back. They don't have enough energy to escape. So photochemical escape is more effective for small planets where the gravity is low. Sputtering, particles can be splashed out of the atmospheres through physical collisions. It requires some particle crashing into the atmosphere. The solar wind can do this if it can make it through the magnetosphere without being diverted around, deflected around by the induced or intrinsic magnetic field. But the solar wind particles are typically protons with the mass of a proton. It turns out planetary particles can also be ionized near a planet. And so an oxygen atom that was maybe produced by photochemical escape, if it gets ionized, now it's an ion, and it'll start gyrating, being carried by the plasma flow, and it may be carried straight into the planet again. If the planet happens to be in the way, now you have something that's 16 times more massive than hydrogen, traveling at almost the same speed that the hydrogen was traveling, crashing into the atmosphere. So the more effective sputterers are the planetary particles themselves that became ionized and crashed back into the atmosphere. I just told you a really great story about sputtering. We have never actually unambiguously detected it happening at planets, but we think that it can be really important for inert chemical species that are hard to get out by other means. For example, argon is a noble gas. It actually doesn't escape very easily. It doesn't escape thermally. It's way too massive for that. Turns out the ion escape rate for argon is really low, but we see these really big signatures in the isotopes of argon in the atmosphere of Mars that suggest a lot of escape of argon has happened over time. And like at least a third of the atmosphere has been lost over the history of the planet, just based on inferring the argon signatures alone. And really the only game in town for getting argon out of the Mars atmosphere is sputtering. So it must have been a really effective process at some point in the history of the planet. Finally, oh, here come the pictures. Ion escape, that's more where I live in terms of my research. I tend to think more about charged particle escape processes. So sunlighter collisions ionize a neutral particle at high altitudes. Electric fields then become available to that particle in terms of accelerating them or energizing them, and can give them enough energy to escape away from the planet. And then any magnetic fields nearby are going to influence the trajectory of the particle in a way that neutrals are not influenced. So this map here at the bottom right shows a statistical map of oxygen ions escaping away from Mars, made by one of my postdocs early on in the MAVEN mission that's orbiting Mars studying atmospheric escape. And so the colors show flux, and the length of the whiskers show the energy of the particles. And this shows A, that a fair amount of oxygen is escaping from the atmosphere. B, that there are multiple different pathways for oxygen to get out. Some oxygen on the day side is ionized and then carried into what we call the pickup ion plume. Some oxygen is ionized more on the flanks of the planet at low altitudes and kind of sneaks around behind and down the induced magnetotail. And some oxygen is part of the extended exosphere that's created by, for example, photochemical processes, really tenuous. The flux is really low, but these neutrals can get ionized far from the planet and then escape back. And some of them will crash into the planet and cause sputtering. So these are the non-thermal processes. So now we've gone through all 5 or all 4.5 in my book: thermal escape, hydrodynamic escape, photochemical escape, sputtering, and ion escape. Thermal escape is thought to be most effective for low mass species, hydrogen and helium. Photochemical escape is important for oxygen and nitrogen and carbon. Sputtering for even more massive particles. And ion escape, anything that can be ionized, but typically we're talking about O+, O2+, CO2+, when we're studying Venus and Mars. Even for Earth, we're talking about O+, and sometimes H+. Okay, a little more on ion escape. My animation game was weak on this, this slide set. So the generalized Ohm's law is what has me putting what some people consider that there are 3 or 4 or 5 different ion escape mechanisms. But the generalized Ohm's law has me lumping them all together into just ion escape. Because an ion has a whole history, a whole past it could tell you, and different electric field terms can be important at different times as that ion is escaping away from a planet. When it's down low, it turns out electron pressure gradients can be very important for providing a boost to that ion to move upwards. And I hope you'll learn about electron pressure gradients tomorrow in ionosphere. Maybe not. When you're far from the planet, the pickup term, V cross B, that tends to be stronger than the other terms. And any place the field is curved or kind of wrapped around a planet, then J cross B becomes an important acceleration term as well. And so it turns out that in my view, and in the view now of the MAVEN team, combinations of mechanisms can accelerate ions, and it's kind of an arbitrary distinction to distinguish between each one of these 3 things. Okay, a few comments on ion escape. And a meta comment, I feel like I'm going so much faster, and I don't know why. It might be the sugar, but I'm sorry if I'm going too fast. Number 1, I already made this point. Different escape mechanisms are important for different species. So if you're only studying one, you're not getting the full picture. You may be a specialist in one, and people are specialists in just one, but make friends if you want the full picture. Number 2, the importance of a process can vary with time. We don't think argon sputtering is important today at Mars, but our inference is that it was very important in the past. This can happen with any of the processes. As a function of time, their importance can change. Not all processes operate at a given planet. Photochemical escape doesn't happen from Venus. That doesn't mean the photochemistry isn't important, because that's populating an exosphere, an oxygen exosphere around Venus that could then be ionized and escape via ion processes. So it doesn't mean it's not important, but it doesn't result in escape directly. And then finally, a topic that's become very close to my heart in the last 8 years, 10 years or so is magnetic fields and their role. So they should directly impact some processes, like ion escape. How it impacts it, we'll discuss. While other processes are either indirectly impacted by magnetic fields or not impacted at all. And right now, all of this is an open question. It's a frontier of the field. Okay. Let's not do this, because this is a calculation question. And I want to talk at you more. But let's kind of do a mental pause and discuss how you would go about computing this. Have you been asked to turn an escape rate into something like how much atmosphere was actually lost in terms of pressure, or how much water was lost in terms of depth? Have you been asked to do that in the last week and a half at all? Okay. So let's say 10 to the 26 oxygen atoms are leaving a planet every second. Okay, that's like 1,000 moles. That's more like 200 moles are leaving every second. If that happened every second for 4 billion years, how would the atmospheric pressure of that planet change if it was a CO2 atmosphere? So what kind of things would you have to do to figure that out? Okay, so figure out how much oxygen was lost. So basically multiply by 4 billion years, right? And then turn that number into a mass, I think you said, if you know what its atomic number is. Yep. So the atomic number is 8. which means it's 16 proton masses worth of stuff, or it's 8 grams per mole. Either way, you can get the total mass of oxygen that is left over 4 billion years. How are you going to turn a mass of oxygen that is left into a pressure? Ideal gas law is an option. Something even simpler. I'll give a cryptic hint. In this room, we're all basically physicists. So it's really fundamental first year physics. What is pressure? Is force per area. Okay, and you just figured out a mass, right? So if you have a mass, you can get a force. You just multiply the gravitational acceleration, divide by the surface area of the planet. So you can get an escape rate, make some silly assumptions that that escape rate has remained constant for 4 billion years. And when you do that for this planet that is Mars, you find that 100 millibars of oxygen would have been removed over 4 billion years. Turns out this 10 to the 26 per second is probably a pretty high estimate for today's escape rate. But over time, we expect that escape rate to have been higher and higher and higher in the past. So then you've done the calculation, you've done the heliophysics, now comes the interpretation. Is that enough to change climate? Go talk to a planetary scientist at that point. Is it a lot? Is it a little? No, Earth's atmosphere is 1 bar. And it turns out for Mars, to get the temperature up to the point where we could probably explain the presence of riverbeds and lakes, we need at least half a bar. And some people think we need 1.5 bars to 3 bars of atmosphere to have been there in the past. So maybe other processes were important. Maybe some of the atmosphere went down and some went up. But this is where pulling in people from other communities becomes important for kind of answering the question. Does that make sense what I did? Okay. More awake or less awake than you were 2 minutes ago? Same awake. All right. Observations of escape. Oh, not doing that badly. I thought we'd all be tired at this point, so this is just sort of let the next few slides wash past you. This could have been really long, this part, but I just kind of threw a bunch of stuff all in one spot. So atmospheric escape from Mars. There have been multiple spacecraft that have measured escape or inferred escape by the different processes, but really the best game in town is MAVEN. And I'm not saying that because I'm a part of the team. I think the best measurements of atmospheric escape from any planet in the universe are happening at Mars from MAVEN right now. The instruments are the most capable that have ever been flown for atmospheric escape measurements. We have better measurements of escape from Mars than we do from Earth right now, when you think about the whole suite of processes. So we have measurements of thermal escape. These are indirect measurements. We use ultraviolet observations of hydrogen. Anywhere you see white to blue in this image, that's hydrogen scattering light into the instrument. From that, you can determine how the hydrogen intensity is changing as a function of height. And then you can back out what the density must be at the exobase of the planet. From how it changes with height, you can infer the temperature, because temperature determines scale height. You have the density and temperature at the exobase, you can compute escape rates. And it's more complicated than that, but thermal escape of hydrogen around 10 to the 26 per second. Photochemical escape of oxygen, a different way of doing this. And I give you one example, I won't give you all the examples. 1 to 5 times 10 to the 25. Here, photochemical escape fluxes are shown as a function of solar zenith angle around the planet to show that most of the photochemical escape is coming from the day side, where the photo part is. So that makes sense. Sputtering is based on a model. These are not observations, but the model takes into account how many charged particles are crashing into the atmosphere with what energy, and then computes sputtering of argon and CO and N2 and oxygen. Notice these rates are around 10 to the 23, maybe 10 to the 24, which is why these signals get lost in photochemical escape of oxygen at 10 to the 25. It's not like the oxygen atoms that we're measuring wear name tags that say I was sputtered or I was lost by photochemical escape. So you're looking for a really tiny signal in the middle of a really large one, and that's what makes it so hard. And then ion escape I already told you about. Venus, it's big enough that thermal escape of hydrogen is unimportant. The rates are very low for hydrogen. I already told you photochemical escape of oxygen doesn't happen from Venus. It's big enough that the energy that those oxygen atoms acquire isn't enough to escape the planet. Sputtering, we don't know. We haven't measured it at any planet, but it should be happening. What we have measured fairly well is ion escape, and that's using mostly the European Venus Express spacecraft that was at Venus from 2006 through 2013, something like that, and then burned up in the Venus atmosphere. So we get an escape rate that's roughly comparable to the escape rate from Mars in terms of charged particle loss. Pretty comparable, even though the planet's a lot bigger. Earth, photochemical escape of nitrogen and oxygen, unimportant. Earth is too big for them to escape photochemically. Sputtering doesn't really happen. The solar wind isn't going to get in there and directly impact significant portions of the atmosphere. And any ions that are escaping are going out the cusp regions. And so they're not getting kind of redirected back into the planetary atmosphere. So we rule those out. Thermal escape of hydrogen is important. Turns out ion escape of hydrogen is roughly comparable to the thermal escape. It could be, a factor of 3 or 5 lower. It could be a factor of 3 or 5 higher, but they're comparable to each other. And then oxygen, the ion escape is around 10 to the 25, maybe 10 to the 26. So a factor of 2 to 10 higher than for Venus or Mars. Escape here is used very loosely because really what's measured is outflow or upflow in the cusps of oxygen. That oxygen could, guided by Earth's magnetic field, never escape the planet. It could be trapped in Earth's magnetic field and gyrate back and forth in the magnetic field and diffuse. It could be trapped in the magnetic field, come all the way back around and crash into the atmosphere at the other pole. And so I once asked Bob Strangeway what fraction of the measured upflow actually escapes. And he said very confidently 50%, plus or minus 50%. So that's a frontier right now. And there are people in the Earth community who disagree violently with that statement that I just gave you. They think they know. And I don't have enough expertise to adjudicate between Bob and them. Variability in escape, this could be a whole nother talk. Escape varies when the inputs from the star vary. So for Earth, as the pointing flux in the solar wind, the DC component of pointing flux, as that increases during one single CME event, then the upward ion flux in Earth's cusps also increases. This is based on fast observations in Earth's cusp regions. That's from Bob Strangeway. From Venus, this is a little harder to tease out. Compare the left plots to the right plots. The sun is over on the far right, flowing past the planet and grabbing oxygen as it goes. And blue means lots of oxygen. Red means not so much. Okay. And it turns out during solar maximum, there's more oxygen loss and more hydrogen loss from Venus than at solar minimum. As the EUV flux changes, the escape rates change. Bottom left is a former postdoc of mine for Mars, ion escape, showing that as the EUV flux from the sun increases, escape increases, but trying to figure out what would happen long ago in the sun's history is difficult. We don't sample really high EUV rates in the present day. And it's unclear whether these escape rates are leveling off or will increase without round. And we don't have time to talk about supply limited escape versus energy limited escape. But if you remember those buzzwords, that, you know, Mars is right at the hairy edge between being really limited and how much it can ever push out at any given moment. I didn't talk about the last one, but I already pressed the button, so there's no going back. All right, influence of magnetic fields. So now we're getting into my more recent research, even 8 minutes earlier than I told Nick. So that's good. My current research interest was sparked by Bob Strangeway, who was one of the first people to notice that the ion escape rates from Venus, Earth, and Mars were all kind of very close to each other. Within the uncertainties, you could call them the same. And wants to know if a magnetic field is so darn important, then why are the escape rates from the 3 planets the same? And he presented this at AGU in like 2008. And I was still a research scientist at Berkeley then, and saw his poster, and that percolated around in my brain till 2013. When I became more interested, and then maybe 2016 or so, I started taking more definite action to kind of view this as a research area. And now it's the science question that gets me out of bed in the morning, scientifically speaking. So I used to be interested in Mars for Mars' sake. And now I'm interested in Mars as a laboratory for planets in general. And so I do care what happened to Mars in the past, but I'm also kind of equally excited in kind of using the laboratories that we have available to us. And Mars is one of them. So let's talk about this 5-word question that really motivates me. 6-word question. Do habitable worlds require magnetic fields? What's the answer? What do you think the answer should be? Think about it for 10 seconds, and then I'm going to have you hold up a number of fingers that you think that corresponds to your opinion. 10 is not an option. Okay. 5 really isn't an option either. So. All right, you ready to show me fingers? Rebecca, behave. Okay. All right, ready? Hold up the number of figures that corresponds. And if you're holding up one finger, please hold up a polite one. Okay. I see a lot of 4s. See a 1, 4, 4, 4, 4, 2, 2. Okay, thanks. So it turns out the answer is something that I don't know. And that's the end of the day. Any questions? See you later. Okay, let's talk about arguments. Actually, if I had to pick, it would be 4. I think a magnetic field, a magnetized Jupiter, and a magnetized comet are very different situations. And I think there are going to be some regions of the parameter space where the magnetic field is unimportant. And I think, you know, a planet super close to its star, who cares if it has a magnetic field? It's all going to hydrodynamically escape from the energy input there. Even for planets at the same distance from the star, I think other details of the planet will matter. And there's some region of the parameter space for which magnetic fields will be very important, and other regions for which they will not. So my question has been morphed now, has been changed into, for which regions of parameter space are magnetic fields important? Okay. Not just a binary question. So let's do the arguments for and against. The 4 is what I came into grad school kind of learning, not from Fran. Fran didn't say, this is how it is. It just sort of picked it up from the community and the literature. The idea that magnetic fields prevent stellar wind particles from stripping an atmosphere because they prevent access of those particles to the atmosphere. Earth's magnetic field is deflecting the charged particles from the solar wind far away from the atmosphere, and therefore the escape rates from Earth should be lower than if Earth had no magnetic field at all. Total sense, makes total sense. It's really simple physics. Must be right. Unfortunately, the other idea makes total sense, pretty simple physics, also must be right. You don't need the particles to hit the atmosphere. You just need energy from that wind to energize those particles. And so magnetic fields transmit energy via the Poynting flux down the field lines. And that energy is transmitted down the field lines from the solar wind to the atmosphere. For a magnetized planet, one with a dipole field, that energy is much more localized in where it becomes deposited, but it's still capable of driving escape, and escape perhaps in great amounts. So sort of a public talk analogy that I sometimes use is sails on a ship. That sails on a ship allow the ship to capture more energy from the wind than if the ship didn't have any energy at all. And the magnetic field of a planet may allow the planet to capture more energy from the stellar wind than if the planet didn't have a magnetic field at all. So there's some people in the community who actually think magnetic fields increase escape. Another caveat here is that we're talking largely about ion escape, but there are all these other processes that could be important as well. So is the influence of the magnetic field, even if it's real for the escape of oxygen, is it insignificant in the grand scheme? This is another question, and it's guiding some of my more recent research, which I'll hopefully get to here in the last 15 minutes. I still have like 15 minutes or so, right? Yeah. Okay. So there are three ways to approach answering this question that we have come up with as a group. And so our group started off as one of 9 NASA Heliophysics drive centers. So we got a fair amount of money for 2 years, these 9 groups, and something like 25 people in each center. And we got to tackle our question for 2 years, and then we got to go back to NASA and repropose for really big money for 5 more years. And our center was selected for 2 years, but came in fourth place for the 5-year funding, and they funded the first 3 centers. So we just missed. But this story turns out okay. I'll come back. Don't worry. So approach 1 is compare Venus, Earth, and Mars. That's something we tackled. And the idea is, sure, the 3 planets have the same escape rates, give or take, but they're in different environments. At any given moment, they're in different environments. And over time, they're in different environments as well. So you've probably seen NLIL model results before, if not before the last week and a half. I'm guessing you saw them sometime within the last week and a half, where the sun is at the center. And usually in these model results in the community, you kind of focus on Earth. But there are other things in the solar system, including Mars and Venus. And even for this solar storm period, relatively weak or moderate solar storm period in 2017, Venus, Earth, and Mars experience pretty different conditions. So comparing the escape rates that you would observe at that given period of time wouldn't give you really directly comparable results. In addition, the measurements are made by different instruments on different spacecraft, built by different people using different analysis methods to give you the escape rate. And then finally, over time, Venus, Earth, and Mars are subject to different conditions because they're at different heliocentric distances. Venus is closer to the sun, and so it experiences higher solar wind densities. It's kind of at the top of this parameter space plot. Mars is farther from the sun, so experiences lower solar wind densities, and Earth is somewhere in the middle. And then a range of solar wind velocities that's much more comparable. These are only 2 of the factors that can influence escape. It's a very multidimensional parameter space that kind of illustrates what we're talking about. But we do have one result that came from Robin Ramstad in our group when he was a postdoc for me. He took published results of escape rates from Venus, Earth, and Mars, picked his favorite ones. There are many, 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 but he picked the ones that he trusted the most and put them all on a plot. So the vertical axis is the escape rate of heavy ions from Venus, Earth, and Mars. The x-axis is the solar wind dynamic pressure. Okay, and he put lots of traces on his plot that hurt my brain. So I put the color swaths instead to kind of give you a general sense of what's happening. The different traces are for different EUV levels, but in general, Venus doesn't experience low solar wind dynamic pressures. Mars does, and Earth is somewhere in between. Venus responds positively to solar wind dynamic pressure increases in terms of its escape, while Mars is much more complicated in its response. Maybe it's flat, maybe it's kind of up and down, and this is getting into that energy limited versus supply limited thing that I didn't actually talk about. And then look at Earth. The magnetized planet is much more sensitive to what the solar wind is doing in terms of its escape. And it's in a way that suggests that maybe the magnetic field is enhancing escape rather than inhibiting it. Okay, approach 2, study Mars. And not just because I already do that, but I think that Mars has a chance to be kind of a Rosetta Stone here. First of all the escape processes happen at Mars. Second of all, we have great instruments at Mars. And third, Mars has magnetized regions and unmagnetized regions. When you compare Earth to Venus, maybe it's the magnetic field, presence or absence, that's explaining your difference. But maybe it's the CO2 atmosphere versus the nitrogen atmosphere. Maybe it's the heliocentric distance. Maybe it's the rotation rate. It's hard to unambiguously attribute things to the magnetic field. Whereas at Mars, you have a built-in control experiment. One planet with one composition rotating at one rate, and you can look at escape from magnetized regions and unmagnetized regions. A quick interlude, very quick interlude. Did you show these? Okay. This is from my PhD. So my PhD was in 2002. So I'm showing you 22-year-old movies. Oh, nice. That's right. Okay, nice. Yeah, two solar cycles after my PhD. Here are the plots again. And these show that the magnetized regions of Mars are important. Mars has an induced magnetosphere like Venus, but these localized regions of magnetization on the left supply enough magnetic pressure to kind of stick out above the ionosphere. And this is relatively weak. Here come the big whoppers around. And so you have these kind of locally protected magnetic bubbles on Mars when you think about pressure balance. You can also think about magnetic topology, and this is a really naive model. Red is closed field lines connected at both ends to the planet. Blue is open, connected at one end to the planet, and green is unconnected. It's a really silly model, but it just shows that Mars is really interesting and fun and complicated and spinning and magnetic. And look at Fran, she fell asleep again. Okay. Yeah. Oh, I would love to. Yeah, good question. You've already graduated, right? Okay. Nice. Okay, one more interlude. Because of this, aurora happened at Mars, and they're diffuse aurora that happen over the entire day side of the planet because the planet has no dynamo. So solar wind electrons, energetic ones, just crash into the atmosphere, make the whole atmosphere glow. If it's happening in ultraviolet, like you see here, it's also happening at visible wavelengths. And we had the first report of visible wavelength aurora on Mars about a month and a half ago. So astronauts at Mars could look up and see the whole sky light up during auroral events. Not only that, the crustal fields on the night side provide focusing lanes and perhaps field-aligned currents to accelerate particles down into the atmosphere on those crustal fields. So you can see on the night side of the planet these splotches of emission, and this thing right here I know intimately from years of looking at Mars crustal fields. But you have Earth-like aurora in magnetized regions on Mars as well, but just scattered around the whole planet. Totally interesting. Okay, that was all the time we had for the interlude. Now, approach 2. Your brain is so full at this point, but I've had sugar, so we're going to continue. Study just Mars. So I had a PhD student, Tristan, look at oxygen fluxes leaving the planet above magnetized regions and unmagnetized regions. And he started by making maps, and there wasn't really enough statistical significance in those results. The coverage was too sparse. So instead, he organized things on the x-axis by the magnetic field strength. So let's just look at the bottom left plot. Okay. Altitude is the y-axis. Magnetic field strength from the crust of the planet is the x-axis. So unmagnetized regions are on the left, magnetized regions are on the right. And the fluxes of oxygen atoms, ions, are larger above magnetized regions than unmagnetized regions. And the trend with altitude is different above magnetized regions than unmagnetized regions. So a 0th order inference is that the magnetic fields do influence escape, maybe even increase escape for these localized regions on Mars. Okay, approach 3, we can use worlds in a box, big 3D plasma simulations, and many groups have done this, but I had a student who did this as well, Hillary. She used a hybrid plasma model, and you've probably talked about hybrid models. If not, the electrons are MHD and the ions are kinetic. Okay, so you trace those individually in macroparticles. So she put this model to work and gave a Mars-sized planet no magnetic field at all. And then she gave it a 10 nanotesla magnetic field and 50 and 100. She did something like 5 of these, turning up the strength of the magnetic field each time. And then she looked at the magnetosphere, where orange lines are closed field lines and blue are open in each case. And she also looked at the escape rate of oxygen predicted by the model. So I haven't shown you the results because I want you to anticipate them first. So if magnetic fields don't matter at all, you should see a horizontal line. If stronger magnetic fields lead to more escape, this newfangled sails on a ship idea, you should see a line that increases upward to the right. If the traditional idea that I came into grad school with is correct, magnetic fields inhibit escape, you should see a line that goes downward to the right. As field increases, escape goes down. So think about what you expect to see when I reveal the results. All right, you think you're so smart. That's what we see. Which is really cool. And we think we have ways to explain this now. But it suggests that the magnetic field has a complicated relationship with ion escape. There's a sweet spot in the middle where escape is maximized. Okay? And it goes down on either side. One other point to make here is the strength of the magnetic field here is still a couple orders of magnitude away from the actual magnetic field strength of Earth today. The stronger you make the magnetic field, the more you bring a model to its knees. MHD models can now do Earth strength magnetic field as long as you don't get too close to the planet. But hybrid models still really struggle with very strong planetary dynamos. So who knows what happens? I saw you doing this. So who knows what happens as you get stronger and stronger field? Will it do that? Is it just going to decrease?
Dave,
This is what we're capable of.
These were dipolar, right?
Dipole fields.
Right, rather than multipole.
Correct.
Did she do experiments with multipole?
No, a different student, Parker, who you and I know well, he was headed down that path for his thesis, but now he's defending in October and never got there. He got kind of distracted by other really cool problems, but I'm looking to write a grant on atmospheric escape during geomagnetic reversals at Earth, and I'm going to look for a student to work on that grant. Okay, I think we have 5 minutes left, and I just put a ton of slides here in the end because I didn't know how long it was going to take, but I think 4 is probably sufficient here, so I'll just show you those. All of this working on the Heliophysics Drive Center made us realize that we can't answer the question that gets me out of bed in the morning without answering a broader question. If we just focus on ion escape and magnetic fields, we're losing the bigger picture. Like if a magnetic field makes escape decrease, is it increasing in some other process instead to counterbalance that escape? Is the net escape from the planet the same? What if magnetic field isn't the most important parameter? What if the other parameters of the planet make a difference too? So when we reproposed to Heliophysics Drive, we broadened our question And we didn't get selected, but we got close. We were happy. And it turns out that there was still a lot of energy in the team. So we turned around and we re-proposed to a different program at NASA in a different division. So we proposed to ICAR, the Interdisciplinary Consortium for Astrobiology Research. And the funding for ICAR was still a 5-year program. It was 1/3 of what the Heliophysics Drive Center is. So we basically cut out all of the data analysis and focused just on modeling, which killed me. But we figured the data analysts might have really maybe more opportunities to kind of recover that analysis funding. So that's what's been funded now. We just finished year 1, and I can just describe this program to you a little bit and then stop. Our plan is to model planetary atmospheric escape for 150 to 200 different planet-star combinations in a 5-year period. That means 40 per year. And in the first year, we proposed to do 3 because we figured it was going to be really hard and we needed to start slow, build our assembly line, and then do more and more as time went on. So in year 1, we worked on 3 G stars, the sun today, a young sun, and an old sun with a Venus-like planet orbiting. And I'm not going to show you those results yet because the modelers aren't ready to let go of them yet. They're still nervous. But I can show you something else that's happening and how this works. But we call it RAPS, Retention of Habitable Atmospheres in Planetary Systems. It's part of the original Heliophysics Drive Center that we called Magnetic Fields, Atmospheres, and the Connection to Habitability. So the science question is, how do the properties of a planet and its host star influence its ability to retain an atmosphere? So we assembled a team of modelers and still observers are on the team, just not getting paid so much anymore, from 3 different communities. And there are plenty of people that cross over between communities. So I put symbols up there to kind of generalize what community, what box I put them into when I think about them. But it's been really fun getting to know each other, learn each other's jargon, talk about how we view the different problems. We have 4 objectives. Number 1 is we have to compute all the inputs for atmospheric escape. If we picked a young sun, then we need to figure out what the EUV spectrum is from that young sun, either through measurements or models. We need to figure out what the stellar wind is from that young sun. And we need to figure out the interplanetary magnetic field from that young sun. So we have a sub-team that does that. Then with those inputs in hand, we improve and link models for atmospheric escape. And I'll show you on the next slide the kinds of models we're talking about. But one key idea here is that when you get into the exoplanet regime, you can't validate your models anymore. You don't have the observations to tell you if your model was right and wrong, which is a constant criticism of this kind of work. And it's totally valid. And the only thing I could think of to do was to invite multiple models into the team for each part, so that at least we can intercompare models and figure out when they really strongly agree and when they really strongly disagree. And when they disagree, the modelers can work together to tighten the models, or at least we can place rough error bars on our estimates. So that's what we've proposed. Given all that, we're constructing this model library of all 200 cases, and we're building a web interface to it. So anyone in the community can access our results. Anyone in the community can run their own model and contribute the results to us, and we will host them. And also a really talented web developer at LASP is going to develop an interpolation tool where you say, I want to do, a super Earth with this kind of star, and the tool will say, and this kind of planetary atmosphere composition, and the tool will say, well, nobody ran that, but here are the results that are closest to what you asked for. And so here's where maybe you want to start looking. And then finally, we want to use all this to do some calculations. What are the scaling laws as a function of magnetic field strength? What does that curve look like for different kinds of planets? As the planet size varies, how does escape vary across all the different processes? Can we compute sort of an atmospheric lifetime by running different points along an atmosphere's evolutionary path? And most importantly, make predictions for exoplanet observations. An escaping atmosphere will have oxygen escaping or nitrogen or something like that. We can figure out where that escape will happen and what it would look like if you're trying to observe that exoplanet from Earth in transit. And so we have people whose specialty is that, to tie it back to real observations. That's the web interface that doesn't exist yet. And then here's an example of the models, and this is all heliophysics. Everything blue and green is heliophysics here. So we need the inputs from the star. We need the inputs from the planet. We need what the atmosphere is like. And then that feeds into us calculating the upper atmosphere. So we first calculate the thermosphere. We use the thermosphere to calculate the ionosphere and exosphere. We have multiple models doing this so we can intercompare. Once we have that, then we have the lower boundary conditions for the magnetosphere. And we have 5 different magnetosphere models on the team to compute this and compare. There are only 4 listed here, but 1 has joined since. And then we have lots of different ways to compute atmospheric loss by all of the different processes, except for sputtering. We only have 1 way and kind of ran out of money at that point, but it's also, we think, maybe the least important process compared to these other things, at least for right now. So that's where we're headed with this. I mean, I can show you, our model case 0, which is Mars around an M-dwarf star, but I think you get the idea here. And this seems like a good place to stop. This is really kind of where I wanted to get by the end. So I'll stop there.
Yeah, so on your previous slide, I think you said you were looking at 5 magnetic environment cases from like no dipole to an Earth-like dipole. I was wondering if you could give a wee bit more information on how you decided that range, given that we don't actually know what exoplanet magnetic fields look like.
Yeah, the range was determined more by the capabilities of the model than the background science or expectations of the field. We knew we could get nowhere close to Earth's magnetic field strength with the model. So Hillary, figured out that she thought she could go up to 150 nanotesla, and that run was going to bring the CU supercomputer to its knees, but she could get it finished. And then we knew we wanted 0 as an option, and we tried to figure out how many of these we had to populate in between. So that was it. The MHD modelers that I'm working with can go much higher, and they have gone much higher. And they find, at least over this range of field strengths, essentially the same result. The curve looks slightly different, but qualitatively, there's an increase and then a decrease.
Hello. I have 2 questions, if that's all right. First one was, in the observations, how do you said it's hard to distinguish or observe sputtering positively and be sure that's it. But when you make the observation, how do you distinguish that it's definitely ion escape and not sputtering?
Oh, well, okay. Ion escape versus sputtering, that's straightforward because sputtering, we think, is mostly going to be neutrals that are escaping. So if we're seeing an ion, we think it's an ion escape process. It could be a neutral that was sputtered and subsequently ionized before we measured it, but that should be pretty small. But the more problematic one is sputtering versus photochemical escape. And there, the predicted photochemical escape rate is larger by 2 orders of magnitude than the sputtering rate. So I have to be kind of clever. There's a paper that I'm co-author on right now that is submitted to Science that gives kind of tenuous evidence that we think we see the signature. And I can describe qualitatively what that signature is. The photochemical escape should be happening everywhere on the day side, on the illuminated side of the planet. But sputtering should be happening preferentially where you expect the ions to be crashing in. And since there's an electric field in the solar wind that is accelerating ions, there's really 1/2 of the day side where sputtering should be more readily observable than the other. And there is an elevated signal on that side. The error bars are large enough that it is consistent with no trend. But, you know, at 5 different solar zenith angles, every single one of them is above the line with large error bars. So that's what's been submitted right now. You know, the statistics say, don't hang your hat on this, but it's at least suggested.
Okay, thank you. My other question was, in the picture you showed of the sort of hydrodynamic escape, you had sort of like the little graphic showed a tail extending away from, you know, in the anti-sunward direction. Is that actually a real result, or just to make it look kind of like intuitive?
Tell me when to stop. Oh, geez,
way
I'm
back
sorry.
early.
Sorry. Okay, we're getting there. Here?
No, it was earlier than this. Yeah,
Yes.
yes. It looks
Good.
like a comet. Is that actually what it would look like?
For some exoplanets, yes. So those, you know, this is a hot Jupiter exoplanet even. That exoplanet is orbiting in hours around its star. So it's really very, very close to the star. The star, I think this particular star is very hot. And so the escape that's happened, the neutral escape turns out to be very cometary in its morphology. And there are other observations since this where transit observations show a very asymmetric transit that suggests that the planet has some kind of tail of material associated with it. Yeah, so it is an artist's illustration, but it's consistent with what they think the observations are telling them.
So you have mentioned a lot of simulations, and you can use these models to like get the escape rate for exoplanet. So I'm wondering how well the current simulations can match the solar system planets that we can observe.
Yeah, that's a great question. So even though you can't validate for your exoplanet simulations, you can use a model that has been validated for other systems. And the model, the hybrid model that I'm using and the main MHD modeler that I work with have both validated their models against Mars observations and Venus observations to some extent. Neither of the models has been validated against Earth observations. In terms of the other models in the community that are publishing results, I think most or all of those models have gone through some form of validation. Everybody validates in different ways, picks different observations to compare to, but I think everybody can make at least a semi-reasonable claim that they can match some solar system observations. Yeah. But then you're turning the knobs to some setting that model has never been turned to before, and for which you have no observations to confirm you're getting the right answer. This is the big challenge. You have the right physics in the model.
Okay. I also had 2 questions that are kind of unrelated, but so first question. So in this case where this hydrodynamic is, or the blow-off case, for exoplanets, or I guess like things that we can observe where this is occurring, does that usually mean that that planet's going to lose its atmosphere completely, or is there something replenishing all the hydrogen that's getting blown off?
Yeah, really great question. And I don't know the answer, but I'm going to talk anyway with a few ideas. One is hydrodynamic escape, is most effective for hydrogen and helium. That suggests it's most effective for giant planets and in general for primary atmospheres. So the initial gas capture from a stellar nebula. So we think that happened at Earth too, that whole atmosphere was swept away and was replaced ultimately by a secondary atmosphere. So there's a time element here. Just because you don't see an atmosphere on the planet today, or the escape rate is so high that you think the planet will lose all its atmosphere, that doesn't mean it will never have an atmosphere. If the planet is rocky, then there's every reason to think that it can ultimately have a secondary atmosphere. One thing I didn't get to talk about because I was running short on time in the very first lecture, which I'm sure you remember vividly. Oh no, it was the second lecture, which you still remember vividly. The statistics for exoplanets, let's recreate them with my hands. Semi-major axis, distance from the star is here, and size of the planet is here. Ignore the right half of the plot. Just go to the left half of the plot. There were two populations of planets, kind of rocky ones and giant ones. And if you look carefully, there was stuff missing in the middle that was Neptune and Uranus size. And it actually, there's kind of this scoop out in that diagram. That's called the hot Neptune desert. And it's a noticed absence of Neptune and Uranus sized planets close to their host stars. The interpretation of that is atmospheric escape has stripped away the gas envelope around the planet and left just the rocky icy core, which is in that bottom population. So atmospheric escape, people are interpreting atmospheric escape to be important for close-in planets and to affect the statistics of what we're seeing. And what I find incredibly interesting is that there are still some planets in that desert. So what happened to them? Why do we still detect them? How did they keep their atmospheres? Did they have a magnetic field? Are they just passing through because they're migrating? So, you know, that's a fairly interesting topic in the exoplanet community.
Yeah. Okay, thank you. And the second question, completely unrelated. I know Earth is losing water through its atmosphere, but at a very slow rate. And I think it's theorized as well that Mars lost a lot of its water due to it escaped from the atmosphere. So what atmospheric loss process is responsible for planets losing their water, I guess?
Yeah, it's I'm not going to answer that question either because I don't really know. And at least in the present day, people think, well, let me first paint the problem here. I've been talking a lot about oxygen escape through ion and photochemical mechanisms. I talked about hydrogen escape through thermal escape. But when you see oxygen escaping and you have an oxygen escape rate from an atmosphere that's 95% CO2, you're not really sure whether that oxygen came from carbon dioxide or from water. And people that I talk to say that the oxygen that's escaping today should ultimately be coming from water photochemically, but that doesn't always have to be true. It probably changes back and forth. And I think the best way to constrain this ambiguity is to also be doing a better job measuring the carbon escape rate. Because if you have hydrogen, oxygen, and carbon, now you have enough information to start to tease out the relative importance of carbon dioxide and water in the escape. You know, there are arguments that H should be escaping at twice the rate of O to keep the stoic, I can never say that word, the balance between hydrogen and oxygen appropriate as you're escaping. There are other people that say there's no reason that needs to be happening in that way, that maybe over long time scales it needs to balance in that way, but over short time scales, nothing says that needs to happen. So it's kind of an open question, like, are we losing the water? Are we losing the carbon dioxide? How does this change with time? And at least one lever arm for getting better answers is doing a better job measuring carbon escape, but it's more challenging than the hydrogen and oxygen.